Peter here from Tech Explorations, and welcome to this video where I'll guide you through the design of a custom PCB using KiCad 9. I'll start by showing you what the final PCB of this work is going to look like, and I am using the 3D viewer here in KiCad 9 to show you. I've already exported and sent this PCB out to Next PCB, the manufacturer that I've selected for this project, who is also the sponsor of this video, and I thank them for that. So I'm expecting to get this manufactured PCB from Next PCB very soon, so I can just do some hands-on testing. But until that happens, I can show you what the 3D representation of this PCB looks like and just have a look at the various components that are on the PCB. So I'd say that this is a medium complexity PCB. It's 4 layers in it. It's got a bunch of integrated circuits on it. It's powered by an ESP32 C3S2, as you can see up here. The location of the components matters, of course. The location of things such as capacitors and connectors and so on is also important. This is one of the things that I'll be going through in this video. So this is what the PCB looks like eventually. As you can see, it's packed with a bunch of great features. It's an IoT development board designed from scratch. And I'm going to show you how to design this from the very beginning, which has to do, for example, with selecting appropriate components. Here's the bill of materials for the components, a number of components here that I guess non-trivial to include into a PCB like this. We need to go through data sheets and figure out how to do the connections, what kind of circuitry is required to provide power, grounding. There's thermal concerns to look into as well, signal integrity, all those very interesting bits and pieces that are required to consider when you're designing a non-trivial PCB. So we're going to do all that. We're going to continue then with the schematic design. I'm going to go into a little bit more detail about what's happening here in the next segment of this video. So there's schematic design, and then there is the layout here. Now, one thing that I should point out is that designing a board like this in real time takes time. So I designed like this, and assuming that I know what I'm doing, but I don't have full knowledge of all of the components that I'm working with. Some of those components I might be working for the first time ever, meaning that I would have to do a bit of research about them, read the data sheet, understand how they work, and then make them work with the rest of the components. I'd say it would take about 1 to 2 days for an experienced engineer. Of course, don't worry, because in this video I have compressed the entire process to make it fast-paced and engaging for you, without skipping though any of the important steps that matter for learning how to design a medium complexity PCB like this one. Another thing to point out is that I am recording this video in KiCad 9 RC1, so that's release candidate 1. That became available in early January 2025. I'm expecting to see KiCad version 9, the full version, published sometime in late February to early March, but I don't expect any significant or even small changes really between the final version of KiCad 9, the release version, and the release candidate that I'm using for this recording. So you don't have to worry about any differences or changes between what you see in this video and what you will be seeing in KiCad 9. Okay, so having said that, let's have a look at what this board contains, just to get an idea of the complexity that's involved. So I'll start from the right side and then move to the left. So on the right side, you see here the ESP32 C3S2, a system on a chip. Just below it, I've got an SD card. This is, remember, an IoT development board, so you may want to use an SD card to do things such as data logging. Then I've got a flash memory also that can be used to store data from your various environmental measurements. Up here, I've got the BME280 environment sensor. You can use this sensor to capture temperature, humidity, and atmospheric pressure. Right here is an ambient light sensor, so it can capture information about the light intensity. Up here, there's a microphone for capturing sound intensity. Right here, I've got a USB-C connector. We'll be using this USB-C connector for power and for data. There's a couple of buttons on the right side, enable and boot, just to operate with the ESP32. I've got integrated circuits here for the serial communications. So this chip here helps to manage the USB and the serial communications of the board. In this block here, I've got the power regulator circuitry. Down here, I've got the battery management circuitry. There's a battery connector for a LiPo battery plus its integrated circuit for managing charging of the battery. And then finally, I've got a couple of headers here. You can connect those headers to things such as an OLED display or external components. So this is a 4-layer PCB. You can kind of have a look inside, see what's going on in the 3D representation. So 4-layer PCB. I'm going to talk more about the details of the design of the PCB in the next segment of this video. We'll cover everything from the design guidelines and the parts selection to creating the schematic, routing the PCB and preparing it for manufacturing. And I'll also show you how to order your board and get it assembled through Next PCB, who, as I said earlier, is the PCB manufacturer and assembler that I've partnered with for this project. And again, I want to thank them for sponsoring this video. Now, the goal here is to show you the complete workflow in a way that's both educational and fun. And by the end of this video, you'll have a better understanding of how to design your own intermediate level PCBs using KiCad 9, and then how to bring your designs to life with a manufacturer. So grab your coffee or other beverage of choice, fire up your copy of KiCad, and let's get started. Let's take a closer look at the IoT development board we're about to design. I want to give you a sense of the high-level design challenges and the decisions I've made along the way to ensure that this board meets its performance goals and is ready for manufacturing. As you already know, the board is powered by an ESP32 C302 system on a chip right here. And of course, there's a bunch of other components around it, such as sensors and power circuitry, etc. All these have to work together. So one of the key decisions involved is signal conditioning. To ensure clean and stable signals, I've added things such as decoupling capacitors that you can see right here. This is one example at the input, power input of the ESP32. We place those capacitors near the power pins of each integrated circuit, and these capacitors help to filter out noise and stabilize power supply. Additionally, there are things such as pull up and pull down resistors. Let me just find an example. I'm just going to let's go to sensors where I know that I had to use one of those. Yep, so here's the sensor for the BME280 integrated circuit, and there's a couple of pull-up resistors for the SCL and the SDA lines, the I2C interface. So these ensure reliable communication and startup behavior as well. I've also included multiple capacitor sizes, of course. Again, the capacitor sizes, here's one example. Here's another example. This is for the SD card module. There's a variation of values, and we'll find the actual values in datasheets for the various devices. But these capacitors, both ceramic and tantalum, are used to handle high frequency noise as well as low frequency fluctuations. And the placement of these capacitors is critical, especially near components like the ESP32. An example of this, just going to make some room, show you the two windows side by side. You can see here is the capacitor I just clicked on. This is C8, which is very, very close to the ESP32, right on top of it pretty much, because that's what the specification and the datasheet requires. And the role of this capacitor requires its position to be this close to the ESP32. Now, another thing that is important is finding appropriate components. And just to manage my project better, I've sourced most of the components through SnapMagic. So here's one example for the buttons that I use, and here's another example for the USB-C connector. So to save time and maintain accuracy, even though some of those components are available from the KiCad library, I decided, at least for the most important ones, not so much for the simple components such as the resistors, but for the most important ones, I decided to have a look at SnapMagic or some other online distributor of parts, because the point here is not simply to design the board, but also to ensure that it can be manufactured by a manufacturer such as Next PCB. So I've done my research mostly in SnapMagic, and you can see here that this particular component that I've chosen is in stock, which means that Next PCB or your own manufacturer of choice will be able to also find it and include it in the BOM. You can see that in my BOM. This is component. Let's go back to... Okay, so here is the USB component. You can see as I click on it, KiCad PCB editor focuses on the component. And here's the component. This is component J1. If I go back to the bill of materials, you can see that J1 is right here. This is the information that I have included for the manufacturer, and I also include information about the sourcing of that material so that they can find it and order it and assemble the board. Although this is not strictly required, I also decided to include reasonably representative 3D models for all of the components on the board. And usually I can get those 3D models from the same place where I source my parts from. Again, in this case is SnapMagic, but there's many other places as well. So for example, when I look at the J1 USB-C receptor, which is this one here, you can see if I double click on it, I just need to actually get the filter to allow me to select a component. You can see in the 3D models, I've set the 3D model for this particular component to this, so that when I bring up the 3D representation or the model of the PCB, that particular component is modeled. I can see how it's placed on the board. So aside from the satisfaction of visualizing an aesthetically pleasing PCB, I can also visually confirm that there are no physical fit issues. So now let's have a look at some of the other details that I want to show you. It's just as we're getting warmed up for this project. The first thing is in the schematic editor, I've got a multi-page design approach. Because there's quite a lot of components that are involved, I didn't want to put them in the same page. They would end up the project having a gigantic single page that would be very difficult to follow. So I opted for a multi-page approach. So I've got the root page here, which contains power management and battery charging circuits. Then I've got the second page down, which contains the ESP32 and SD card module, USB module here, and the flash memory. Another page is dedicated to the sensors. And then finally, the user interface, where I've got things such as the OLED display connector, breakout for a few unused GPIOs, just so that not wasted. I can connect them to external devices if I want to. And then the reset and the boot buttons. That's pretty much what you have in this last user interface page. When it comes to the layout, let's have a look at the layout editor here. I've opted for a 4-layer PCB. So you can see I've got 4 copper layers. Now, the top copper layer is used for signals. So most of the signals and the signal routes are routed on the top side. You can see additional signal routes in the bottom. And then the first inner copper layer, I've used it mostly for ground. So I've got a large ground zone. You can see it here, this border line you can see going around the board represents a ground zone. Just going to double click on it so you can take a closer look. So this one is ground. And then I've got a bunch of other zones in the second inner copper layer, which is the 3.3 volt layer. I've got a couple actually in here. You can see this one is 3.3, but KiCad 9 also has a zone manager, which allows you to quickly inspect the various zones that have been created. And you can see where they are as well in the various layers. And you can quickly edit the various characteristics and even give them a name so you can search for them later. So I'll show you how to do all that as well. Last thing to comment before we move on to the next segment is that another thing that I've taken a lot of care to do is to select the appropriate widths for the various tracks and the vias. And those decisions are governed by the use of that particular track. So for example, you can see here, this track is quite wide because it conveys power. Essentially, it feeds power to the entire board, where other traces like this one here are much smaller because they convey signals, not power, so they don't need to be as wide. And something similar happens with things such as vias, and also the decision to create things such as copper zones like this one here, for example, in order to enable better power transfer and improve the thermal aspects of the design. So that's an overview of the project and some of the key decisions that went into the design, and it's really worth the time spent at the start of the project to plan and choose appropriate and available components, reading the data sheets to understand the signal conditioning and placement requirements and other requirements, and managing the layout with proper use of layers and copper zones. And all this will help to build a high quality PCB that will be economical to manufacture and of course fit for purpose. Designing an IoT board involves balancing technical capabilities with real-world constraints. So in this segment of the video, I'll talk a little bit about the operational requirements that guided the development of this custom ESP32 board. These are the things that I want to achieve by designing the board and influence me in the various decisions that I had to make. So after that, I'll show you some of the sources that I used for things such as data sheets, the actual physical components that will end up on the manufactured board, and sources for the symbols, footprints, and 3D models, because I like to do all that as much as possible before starting the actual design work in KiCad. There are 2+1 top-level requirements that guided my decision-making process. The first one is that I wanted to create a board that would give me the opportunity to record this video. The topic of the video, as you know, is to demonstrate the use of KiCad 9 in the design of a medium complexity PCB. With that in mind, the second top-level requirement was that this board should contain a modern microcontroller with wireless capabilities and lots of processing power that is connected to a reasonably complete array of components that would require the employment of at least 4 layers on this particular PCB, and the use of typical design techniques for a PCB of this complexity and capabilities. And the +1 top-level requirement following the previous two is that at the end of the process, I'd be able to manufacture this board in a modern manufacturing facility. And in my case, that's Next PCB, who is also sponsoring the video. And you can see that the PCB right now is being manufactured. So I should have it maybe in 1 or 2 weeks. We'll see how that goes. And I'll report on that later in this video. With all that in mind, you already know that the PCB that I'm designing in this video is built around the ESP32, and I selected this MCU due to its high processing power and integrated wireless communication. It's got a dual core architecture, and this ensures lots of available data processing power, making it suitable for handling multiple sensor inputs and performing real-time data analysis. And I also want to use this board once it's ready and manufactured to play around with ESP32's artificial intelligence capabilities. Of course, being familiar with his MCU is an added bonus. This is hardware that I am familiar with. I also wanted this board to be a fully featured IoT board, Internet of Things board, which would be a good PCB design example for this video. So I've added a bunch of sensors, as you already know. There is the BME 280, there's a microphone sensor, and there is a light sensor as well. And these sensors are supported by their own dedicated support circuitry. The board also has power management. So I've designed the board to support 2 power sources. One is directly through the USB 3 port, and another one is through a battery that I can connect via this connector here. And they both have their own supporting circuitry. Then, since this is an IoT board, I wanted to offer a couple of different ways for recording data. The first one is through the SD card right here. So the SD card reader module is used for local data storage, and it allows the system to log large amounts of data independently without the need for the ESP32 to be connected to the cloud. And this is particularly useful in remote or offline scenarios. So when you want to use the data stored on the SD card, simply remove it from the module and copy the files on a computer. And to complement the SD card module, this board also includes a flash memory integrated circuit right here. It's onboard flash memory chip, which provides fast, non-volatile storage for data and firmware, and that ensures that any important data remains intact even after a power cycle. The flash memory can store things such as configuration files and sensor calibration data, and even firmware updates, where the SD card can store data from the sensors that you may want to be able to quickly copy across to a computer, so that the two are complementary of each other. The other thing to mention here has to do with the dimensions and the layout of the PCB. So design the layout to keep the board compact while ensuring that any recommendations from the component manufacturers are adhered to. So the most important component on the board is the ESP32 chip, and that's mostly because of the integrated antenna. And essentially, I started the design of the project, as you'll see later when we get to the layout part of the video, around this component. Especially if we have a look at the documentation for the datasheet, you see that what I'm looking at here is the datasheet for the ESP32 from ExpressIF Systems. You can see that the datasheet offers a few positioning ideas or locations that are approved and correct by the manufacturer. So I studied this document and I concluded that probably the best way to put the ESP32 on the board would be to combine something like this, so position number 3 in this positioning example, with something like this. So I ended up with a design that combines the two. I didn't like the idea of having the antenna poking out too much because I didn't want it to be damaged. I envisioned this PCB eventually going inside a project box. I didn't want this antenna to be out too far, but I also needed to make sure that any components around it would not interfere with the radio capabilities of the board. So I looked at the documentation and came up with this positioning. Again, I'm going to talk more about this later on in this video when we start working on the layout. Aside from the ESP32, my positioning choices had to do with the user interface requirements. So you can see, for example, the buttons here, the connectors tend to be around the edges of the board. And another consideration would be to keep components that are part of the same group together. So you can see the components that have to do with the enable and the boot button are together, close in proximity. The components that are used to implement the flash memory and its supporting bits and pieces are also together, and so on. So again, we'll talk more about all this later in this video. As much as possible, I tried to collect all the bits and pieces that I need for the project ahead of time so that my actual design work is as smooth as possible. What that means is that I do quite a bit of research and spend a bit of time on this to find the components that I need and then collect all these components, both the sources of the actual physical components that will end up on the board, plus information such as data sheets and the libraries that I will need to import into KiCad. Having said that, there's always times where I make a decision of a particular component that ends up being the wrong decision, and then I have to just fix the problem on the fly. That happened in a couple of times with the USB connector. I made choices about the USB connector a couple of times prior to settling to this particular connector, that after going through with the design, pretty much completing the board, I realized that the original decisions were incorrect for whatever reason. Usually it has to do with things such as the availability of the components of being out of stock or some other technical issue, like for example, making it fit on the board alongside the other components. So these are a few things to keep in mind. So what I want to show you here in this segment are some of the sources that I used to do my research to find the components that are needed. So again, I started with the main component, the ESP32, and then I worked my way down to other components such as integrated circuits, connectors, USB plugs, buttons, the SD card module, and things of that sort. And I used online resources such as SnapMagic and snappeter.com. Most of the components that I found come from SnapMagic. And I also used SnapMagic to collect the majority of the footprints, symbols, and 3D models. I'm going to show you more about this in a moment. Aside from SnapMagic, there's also lots of other places, and just as an indication, just for your information, I'll just mention component search engine right here. I used that for a few of the components. There is Kemet.com, DigiKey, Belfuse, USB.org. I use this site to better understand how the USB module works. There's OnSemi for some of the components, SparkFun, Texas Instruments, Silicon Labs, ST.com, and a few more. As I'm going through this research, I always make sure that I record everything in KiCad itself, because I see KiCad as the center of my project. So in KiCad's schematic editor, you can go to Symbol Fields table, and you can see here that each one of the components I've made some notes. So for example, I'm just going to move over. So you can see here, for example, I've just enabled comments. So you can see that I've made a note of the source of the particular component here. So this would be the LED. So you can see I click on it. In the fields table, the item in the schematic diagram appears. So here's a fuse, for example. You can see that I got this fuse from this particular location. So I can always go back, and I can also share this information with the manufacturer so that they have my notes. It just improves communications. So that's one example. Gone ahead of time, of course, because obviously I have completed this project. But most of the work that you see here and the files that I have included in the project directory, I've done all that as well before I actually started the design process. So I didn't have all of these symbols, but I had most of the symbols collected ahead of time. As I went through the project, I realized that I've made a few mistakes or a few things were missing. So I went back to resources such as Snappeter to fill in the missing bits and pieces. Another thing that I also collected in parallel are the data sheets. Much of the work that goes into designing a PCB has to do with reading data sheets, because the manufacturers provides information on how to do the wiring for this particular component. So as long as you understand what you're seeing here, you can literally copy the recommendation from the manufacturer into the design. So the design that you see here in the data sheet is basically what I have followed. I'm just going to show you really quickly. Let's go to the root. Is what I followed right here. So the component that you see here, the LAPO charger integrated circuit, which is U1, is this component here. And I simply followed the recommendation from the manufacturer. So spend a bit of time both collecting the data sheets for the components that you'll be using, and also looking at them and reading them and understanding how to do the wiring as per the recommendations of the manufacturer. Again, most of the work for doing that I did in Snappeter. So if I go back to Snappeter, I'm just going to show you really quickly. Let's say that I'm looking for one of those components. This is the BOM Excel sheet that I'll be sharing as well. Let's have a look. So here's one. See Snappeter. This is the USB receptacle. So I'm just going to search for this connector. Just going to go for the package actually. Search for this in Snapita, and here it is. Click through, and here Snapmagic gives you both a datasheet PDF, which I always save that in the project directory so that everything is together. So I store that file on my computer and keep it in the project directory. I do the exact same thing then for the symbol and the footprint. So I'll go for KiCad 6 or later. So allow the download. So here are the 3 files that are just downloaded, and I've already stored them. So here's a 3D model. Here is the footprint, and here is the symbol. I'm going to show you later how to import these symbols into KiCad so that we can use them. For now, I'm just storing them into my project directory. So I do all that, and once I'm confident that I've got pretty much everything that I need, or at least most of what I need, I begin with the project. So what I've got here is KiCad 9. I've got the release candidate version. I just updated this morning, the latest available version, and I'm just going to show you where I got it from. I'm running macOS, so this is the location where I downloaded this particular file here and then installed it. And on my computer, I'm just going to show you one more thing. I'm running 2 versions of KiCad. This one is KiCad 8, which is the official version, the stable version that is available at the time I'm recording this video. And of course, in parallel, I'm running KiCad 9 for the requirements of this particular video recording. You can run these 2 versions, or as many versions as you like, really, in parallel, no problem at all, as to how you organize your KiCad instances. All right, so as we've learned already in the previous few segments of this video, I've already taken a bit of time through research and preparation for this project and worked out my bill of materials. And in a realistic situation where you're just starting fresh with a new project, this BOM is probably not going to be the final one. You'll be working through the details as you're working through the project. But in my case, since I've already rehearsed this video and I've pretty much completed the entire process a couple of times prior to actually recording this video, I have a pretty good idea of the components that are going to be in it. And so I've got the benefit of the bills of material being pretty much finalized. Just keep in mind, in real life, if you were working on this project for the very first time, just like I did when I went through it for the very first time, I only had a partial set of components here. I had the major components, such as, of course, integrated circuits and the microcontroller unit, the ESP32. I had a good idea of the rest of the components, such as the diodes and the buttons. And then I went with more generic options for things such as the resistors and the capacitors. In previous segments of the video, I explained that as part of my preparation, I went ahead and used various online resources, mostly Snapita, but a few other resources that are also available in order to find, download, and make available, especially the footprints and the symbols, but also the data sheets. So I spent a lot of time reading through data sheets before I even started drawing anything in KiCad. And that's, again, part of your preparation. I estimate that when I add all the time that I put in to prepare for the project, the total amount of time spent would be about 5 to 6 good working hours to collect all of these files. Okay, so let's get started with KiCad. I've already started the application and I'm going to go into a new project. And I'm going to save this new project in this directory that I've already started. And because the directory already exists, I'm just going to uncheck this option to create yet a new folder. So I just want KiCad to store all of its files in the directory that I've just selected. So I'll give it a name, KiCad 9 ESP32 demo project. And save. Yep, the selected folder is not empty. I'm fully aware that there's content in this directory. And yes, I want to continue. So there's the new files just created as part of this new project. The next thing I want to do is to do some basic setup. I'll do that under KiCad settings. There's a few things I want to check. Things such as the high quality anti-aliasing just makes everything look better in the schematic and the drawings. I'm going to jump into this schematic editor and have a look at a few things here, such as the display options. I tend to go with the defaults there. Now, under grids, there's a couple of things I want to double check as well. I've got the 100, 50, 25, and 10 mils, which is good. And then for the fast switching, I've got 50 mils and 25 mils for that. And all the grid overrides as well look good. All right, so that's okay. Again, all this is really personal preference. That tends to work better for me. And I'm going to go to the editing options and have a look inside here. All this looks okay. Annotation options also look good. Just going to skip the rest. I'm just going to accept the defaults for everything else and go into the PCB editor and have a look around here. All this again looks fine as it is, and just notice I'm going for full window crosshairs. It makes it easier to align things together when I'm using full window crosshairs, and the same thing happens with the schematic editor. Then for the grids, these are the grids that I've already selected and created. Your list of grids is probably going to be much smaller if your KiCad installation is new, but in my case I've added a few additional grids, and these are my grid overrides. Origin axis and editing options defaults work fine. Click OK. Next up, have a look at the plugins. I'm just going to go into the plugins and content manager via the button here. Just want to show you the plugins that I've got installed. So in this project, I'm only going to be using a couple of these plugins. I have a new, fresh installation of KiCad. I tend to install these plugins, which I tend to use from time to time. So there's Interactive HTML BOM, PCB Action Tools, Round Tracks, works really nice, Free Routing, and the HQ DFM, which I'll be using at the very end of this project to test my board before submitting it for manufacturing. And I've got a few other plugins here as well. Out of this entire list, I recommend that you install at the very least the free routing plugin and the HQ DFM. So next up, let's go into preferences and install the symbol and the footprint libraries. Remember that I've already collected those libraries here and stored inside the same project directory. So I'll start with the footprints. Notice that I've got an option here to import those libraries globally, so for all future projects or for the project specifically. And I'd like to have a better control of the libraries for each project, and I tend to go for the project-specific libraries option unless there is a library that I'm installing that I know I'll be using across multiple projects. In this case, most of the components I'll be using will be specific to this project, so I'm opting for the project-specific libraries here. So then I'm going to use this option here to select a KiCad folder with KiCad mod files. So click on this button. Then I'm already in the project folder. Go into libraries, select footprints, just at the folder level, and click on open, and that's it. Just going to change the name here. I'm going to call that ESP32 Project Libraries. This nickname will make it easier for me to recognize that I'm selecting a footprint from inside this particular project footprints library. And click OK. Let's do the same for the symbols. So for the same reason, I'm going to go for the project-specific libraries. Click on the folder button and then go into symbols. Unfortunately, I can't select all of the library files in this directory. I have to select them either one by one and click on open, or do a multi-select. That's what I'll do. So select the first item in the list, hold the shift button on my keyboard and scroll down, and while I'm holding the shift key, click on the last item to highlight everything, and then click on open. And you can see that now all of these symbols and the symbol libraries have been selected, and they are under the project-specific libraries. And click OK. And now I'm ready to get started with the schematic. Here's the blank schematic editor, and the plan here is that I'm going to have a total of 4 pages. In the first page, I'll have the USB and power related components. Then in the second page, I'll have the ESP32, the module, plus the USB to UART converter and a couple of LEDs. Then I'm going to have another page for the sensors and finally another page for the user interface. So I'll be creating these pages as I go and then providing connections in between the pages. Let's start dropping some components. Start with the sheet page settings. I just want to add my date here. Give it the title. So there's going to be ESP32 sensor board. You can add more details there as you wish. All right, so you can see that information, the text appears down the bottom. Let's begin with the USB receptacle. So I'm just going to either click on this button right here on the top right toolbar, place symbols, or use the A hotkey to bring up the symbol chooser. So remember that here I'm using, or I want to use, the SS52400 receptacle that I downloaded earlier from SnapMagic. So I'm just going to search for that. SS, there we go, came up. That's the one that I want. I can either double click on the item or just click on OK. And I'll place that around here. I'm going to rearrange my symbols a bit later. The next major component is the LiPo charger, and I'm looking at my bill of materials, and the item that I'm looking for is this one here, the MCP7387. The A key to bring up the chooser, and I'm now going to search for MCP7387. And it's this component here, so click OK and I'll place it around there. Next up, I've got the voltage regulator. So again, click anywhere in the sheet, and looking at my BOM, the regulator is this item right here, the LM1117. So search for that, LM1117. Click OK, and I'll place it around here. So I'm already starting to create areas where all related components will be going together. So this part here is going to be where all the USB-C related components are going to be. This area here is going to be where all the LiPo charger components will be. Here is the regulator. Move that up a little. And I also have the battery connector, so I'm going to add that as well. So the battery connector that I want to use is the JST connector. Looks like that. Click OK and place that right there. For each one of those components, I need, of course, the supporting components for the circuitry. I'm going to drop all the resistors that I need on this sheet, and then I'll continue with capacitors and LEDs. So let's start with the resistors. I'm going to hit the A key on my keyboard. Here in the chooser, I'll select R. I've already done it, but I'll select R. Double click on it, and I'm going to start with, say, here. I'm going to drop this resistor right there where it's going to be eventually connected, and then double click on it to change its value. So this is going to be a 10 kilo ohm resistor. There's going to be a pull down resistor. I need one more of them. So I'm going to type Command D on my keyboard to create a duplicate. And I'll drop it right here, and I'm going to move the designator and the value a little, just so that there's no overlap. And this one is also going to be 10 kilo ohms, so that's fine as it is. So next up, let's have a look at the resistors around J1. So I'm just going to type A, bring up this resistor. I'm going to place it around here. This is going to be another pull down for the C2 line, and the value for this resistor is 5.1K. I marked it down as 5K1. I could have done it something like this, for example, 5.1K, but I find that the dot sometimes is not easy to see and therefore can be misread. Whereas if I do something like 5K1, it's much easier to get the information correctly that this is a 5.1 kilo ohm resistor. And also, if you're wondering where I get the value for the particular resistor, I'm just going to connect it right now just to make it a bit more clear. So this is a pull down resistor for the CC2 line. Then the answer is the USB datasheet. And I'm going to have another similar resistor on the other side for CC1. It's just going to be another 5.1K resistor that will go right there. Of course, to draw a line, which represents a wire, I simply click on the pin and the drawing tool will automatically start drawing a wire. To stop drawing, you can just double click, or if you want to cancel the drawing operation, just hit the escape key. All right, I haven't finished the wiring here. I'm going to add the ground symbols a bit later. So also, if you want to move things around, you can just place your cursor on the thing that you want to move and then just type the M key on the keyboard, or you can just click with your mouse and drag. Notice that when you do that, the wire that I've already drawn, it gets interrupted and then I have to redraw it. Alternatively, you can see if you do a right click to bring up the context menu, there is the drag option, which you can use the G shortcut to activate, and that ensures that any wiring you've already done is not being cut or removed. And then click again to finish the drawing. Okay, so I've got R1, R2, R3, R4. I'm going to go back to my U1 component. So I'm going to add a couple of additional pull down resistors. So just the A key again, the R is going to be 1 here. And I'm just going to duplicate this one here, another one. They've got different values. So the R5 will be 2K and the R6 is going to be 20Ks. And while I'm at it, I'm just going to do the drawing as well. Here's a wire for TE negative and the therm. And these two will go to ground. I'll do the ground now, so don't forget. So for some reason, my chooser, the power symbol chooser, is not coming up properly formatted, and this pane on the side is just folded. Anyway, it's not hard to expand it. So here I'm going to pick up the ground. I can just search for GND. This is just another symbol, but KiCad provides a separate menu item here on the side to make it easier to find. So that's a ground, and I'll draw a line to connect it to R1 and R2. So these two are pull down resistors. And I've got the same thing down the bottom for R5 and R6. Duplicate that ground symbol, connect the two resistors together, and finish the connection like that. And the R5 goes to prog 1, and R6 goes to prog 3. Now, if you're wondering again how I know how to do the wiring here, again, the answer is the datasheet. So this is the MCP 73871, and you can see in the datasheet there are example typical applications, and I'm simply following the example that's given to me by the manufacturer. Nothing fancy here, and I'm not making these up. This is what the manufacturer suggests. On the other side of this U1 component, I've got some indicator LEDs. So I'll bring up a few more resistors first to protect the LEDs from overcurrents. So this is going to be R7, and this is going to be 470 ohms. So I'll duplicate it a couple of times, R8 and R9, and these go to these 3 pins. So R9 will go to PG, R8 will go to SDA1, and R7 will go to SDA2. So these indicate that the battery is either charging or it is already charged. For the LEDs, I found the components that I want to use from Snapheater, and as per my BOM, you can see I've got 3 different types. I've got a red, a green, and a blue. I've already imported those to KiCad, so I'm just going to search first for the red one, which is the LTST red, this one right here. So import that into my schematic, orient appropriately, and that's done. I want one more. I'm not going to duplicate this because the next one I want is a green one. So back to the chooser, and this one is a green. Okay, like that. I'm just going to make a little bit of room between those. And I've got one more. The last one is going to be the blue. right there. I can type the M key on my keyboard to move things around. All right, and then finish with the connections. One goes there, there, and there. The bottoms of the LEDs or the anodes of the LEDs are connected to the same place, which doesn't yet exist. That's a net that I'm going to call 5-volt USB, which doesn't exist yet. As I said, I'm going to connect it in a minute. So I'm just going to leave these wires unconnected for the time being. I'm just going to add a couple of grounds. So I'm just going to duplicate this ground and move it over here and finish this wiring here. Do one more and finish that wiring right there. A couple of other grounds that I'll connect while I'm at it is this. So G and D, just duplicate and connect A12, which is GND A2 to ground. There's also one more ground. I'm just going to go straight there instead of introducing new symbols. So these two pins also go to ground. There's one more ground up here. Like that. Move that down a bit. And of course, one more on the other side. Right there. Done. I'll continue my work with the USB connector before I move to the other components. I think at this point I've got enough already set up here to allow me to complete one part of the schematic before I move to the other parts. I'm just going to make a little bit of room to the part of the schematic that I'll be working for the next few minutes, and that is the connector. On the connector, I also want to include a couple of things, especially the polyfuse to help protect my board from overcurrent. So that polyfuse is connected right there on the VBus B1 pin. I've already selected the fuse to use, so it's this one right here. So I'm just going to search for bell fuse, and the component should already be available there. Search for bell fuse. Yes, it's right here. So that's the one I want to use. So click OK. I'll place it right here. I want to have a straight line, so I'm just going to make a little change. I'm going to remove that line. Actually, I'm going to remove all of this and move the ground a little bit closer to the pin and connect it in like that. Now for the fuse that gets connected to this pin right there, that's where power goes into from the USB bus. And then on the other side, again, that's the USB bus that comes from the power circuit. Next, I'm going to add a capacitor that will act as an input filtering capacitor. Add a new component. It's going to be just a regular capacitor, nothing fancy. I'm going to place that, say, around here where there is space. And the value for this capacitor is 0.1 U or microfarads. I use G to move that a little more. Okay, here is a good place to connect it to the polyfuse, just like that. And I'm going to duplicate the ground symbol and connect it right there. Just going to make a little bit of room. Select all this together, type G, and move everything a little bit to the right. So I think that's it with J1 and wirings. I'm going to connect the remaining pins to particular nets, or I will mark them as unconnected. To mark a pin as unconnected, I'm going to use this button here, place no connect flags, and that allows me to just click on a pin that I want to tell KiCad that is not going to be connected to anything, so that will suppress any error messages later on, like that. So SBU1 will also be unconnected, and then up the top got these two that will be left unconnected. On the other side is B2 and B3, B8, and then B10 and 11. So let's save at this point. Speaking of save, if you go to KiCad settings, have a look at this area here in common project backup, automatically backup projects. So actually I want to make sure that I don't lose any work. So I'm going to have lots of backups, let's say 10 per day, every 5 minutes. You don't want to lose any work, and since I'm working with a release candidate version of KiCad, I'd rather be safe than sorry. I've got my J1 almost finished. The next thing that I want to do is to start creating some nets. So I'm going to use the net label tool right here. You can use the L shortcut for label, and with that you can start creating labels. So I'm going to have a net named bus. Just type the R key to rotate it and orient it appropriately, and this is going to be VBus. DP1 and ND1, so DP for positive, N for negative. This is going to be a differential pair for the data pins of the USB connector. So click here to bring up the label properties, and this is going to be USB DP or data positive. So it goes in here. And I'm just going to duplicate that. Hit escape, select the label I want to duplicate, and type Command or Control B, D. Click that to connect it to A7, and then double click again to bring up the properties and make that P and N for negative. So I've got DP and DN. Then the letters here at the very end of the two labels is important because P and N indicate to KiCad that this is a differential pair, and we are going to use this feature to do the wiring later on in the layout. There is also one more VBus. I'm just going to duplicate that and connect another VBus wire right there. So VBus A2 and VBus A1 connected to the same net. On the other side, I've got two more differential pairs for data. These are short-circuited. They're physically connected in the connector, so that's why they're part of the same net. So I'm going to duplicate DP, flip it over on that side, and it's going to be a P right there, and then the N or the negative of the differential pair right there. Another VBus label right there, duplicate, done. This is going to be VBus 2, and finally I need to mark this wire as a member of the VBus net. So this is going to be VBus B1. There's one more net to create. I'm just going to use the L key for that, and this is going to be the plus 5 volt USB net, which goes there. Using the G key to move everything a little bit further in. Okay, that's it. This is the USB connector. I'm going to do another check a little later, but I think for now that's enough work. So I'm just going to draw a little box around it and give it a label just to make it easy to see when I'm quickly looking at the schematic diagram that this is a block of components that belong together and they play a particular role. So this is a USB connector, like that. I'm going to continue now with this part of the first page of the schematic. Now that I have the VBus, 5 volt VBus, I'm just going to duplicate it and finish up the wiring of the LEDs. So these go like that. And I'm just going to mark that here as the VBus. Now I'm going to continue to implement the wiring for the LiPo charger integrated circuit just by following the recommendations of the datasheet from Microchip Technology, the manufacturer of this particular integrated circuit. So I'm just going to continue essentially copying what I see in the datasheet. So I've got one more 5 volt USB pin, Prog 2. I need to bring that up to 5 volts. For VBAT sense, just going to shorts that with VBAT and then mark this net with a name. So type the L key, and this is going to be the VBAT net. Mark it like that. For out, this is the reason for the existence of this particular chip, is whatever comes out of this pin. And I'm going to create a new named net with the name plus 5 volts. So that's what comes out of this particular chip. So on VSS, I'm going to connect this to ground. You can see that's what the datasheet is telling us to do. So this is going to go to ground. Just going to duplicate ground symbol, orient it like that, and mark it like this. Now, one thing to keep in mind, I'm just going to bring up the symbol and having a look at the VSS. You can see that that is marked as a power input. So if I leave my schematic like this, so VSS directly connected to GND, I'm going to get an error message from KiCad later on when I do the ERC check. So to prevent that from happening, I'm going to go back to the power symbol chooser and search for a flag, this power flag here, and attach this flag to VSS, and that will suppress that error message from KiCad and indicate to KiCad that yes, I do know that this is a power pin and I've already taken care of that. Don't worry about it. Let's go down to the bottom. Pin 18 is in, and that's where we apply the 5 volt USB power. So that's coming out of here. VPCC, that's connected right there. And we're going to copy the flag and plug that into here. So basically pin 2 and pin 18 are connected to the 5 volt USB input power. Here I also need a filter capacitor, so I'm just going to bring another capacitor and drop it in there. This one is going to be just 1 U, and I'm going to change the reference to C6 just to keep in sync with my notes here, because I'm going to have a few other capacitors with different IDs. I want to be a little bit more in control of the designators. So normally I will allow KiCad to come up with whichever designator it wants for new components that I'm dropping on the schematic sheet. But in this case, I want to have a little bit more control, as I said. So I'm going to go ahead and rename this capacitor to C6. Then we'll connect that to ground. Done with that. Let's have a look. Anything else? I've got CE up here, which also needs to go to 5 volts USB. I think this part of the schematic is done. So hit escape, select the whole thing and move it down a little. And then put a box around it to indicate to the reader, or myself in this case, and you, that this is a set of components that belong together. And I'm going to put a label here as well. And this is going to be the LiPo charger. Done. The next thing is the low dropout voltage regulator. I'm going to follow the instructions from the datasheet, and in particular, I'll implement a variation of this recommendation here for a fixed output regulator. On the VIN side, I need 2 capacitors. One of them is going to be ceramic and the other one is going to be tantalum. So this one is the ceramic capacitor. Place it right there, double click to get its properties, and this is going to be a 0.1 U capacitor, and this is C2. That's correct. Again, just keeping in sync with my notes. I also need a tantalum capacitor, so A key again. The tantalum is basically an electrolytic capacitor, so I'm just going to search for C, and that's a polarized. I'm going to use this polarized capacitor symbol for tantalum and place it right there. Double click, change the value to 10 microfarads, like that. And I'll have the exact same thing on the other side as well. So I'm just going to select these 2 and duplicate them and move the group of the 2 capacitors to the other side. Just going to change the names. I want this to be C5 and this to be C4. So I'm going to have C5, which is going to be 0.1. Just going to move it on the other side. Just keep a note here, the placing of the capacitors is important. So just flipped the ceramic with the electrolytic capacitor because I want the electrolytic capacitor, tantalum in my case, to be closer to the pins on the integrated circuit that it will be connected to. In this case, is going to be the 2V out pins. In other words, the proximity of components to other components is important in the schematic just as it is in the layout. When I see that C4 is close to V out 2 and V out 4, I know that I need to place C4 very close to those 2 pins in the layout as well. V in goes there. So I've got the 2 filters and I've got the ground. Just going to duplicate the ground symbol, place it right there and finish the connection on that side. And then there's a label. I'm going to place this label is going to be plus 5 volts. So 5 volts goes into this regulator and 3.3 volts comes out. On the other side, I'm going to use a power symbol for the output. So on the output, I have 3.3 volts and there is a symbol for that. So I'm going to use that instead of creating my own custom label. So that's going to be this symbol right there. All right, so Vout2 and Vout4 go to the same place. We've got 3.3 volts coming out of this voltage regulator. And for the filtering part, we also have these two capacitors. As I said, C4, I'll be connecting it very close to those two pins to improve the performance of the filtering. And just like I did up here with the power flag, I'm going to use the same power flag here to tell KiCad that I'm aware that this particular component, we have a look. If you have a look in the symbol editor, you'll see that these two pins are power inputs. I'm telling KiCad that I know about that fact and it doesn't need to worry about bringing up an error message when I do the ERC check later on because it's been taken care of. And I've got the ground component as well for these capacitors. And there's one more ground. I'm just going to give this one its own ground actually, just duplicate. Just for clarity, I could have connected this ground pin straight here and share the same ground symbol as the capacitors, but I wanted to be a little bit independent in this case. I think it looks better as well. So I'm just going to leave it like that. Now, one thing I'm going to improve here is I just realized that I've got a 5 volt label here and a 3.3 volt symbol label on the other side. I just want to be consistent. So I'm going to remove that manual or custom label and replace it with an actual 5 volt label from KiCad. Actually, I'm going to use one of those. So 5V, I'm going to use this label like that, just rotate it. Okay, that's better. Select all these, type G just to move things in a bit. And I think this block of components is now complete. Just going to move it all up a little like that and put a box around it. This is going to be the low dropout, or LDO in short, voltage regulator. I also have the battery connector that's going to be quick to connect, and I'm also going to add a power indicator LED in a moment. So let's have a look at this component, the battery connector. I'm going to rotate that so that the pins face inwards. And on one side, I want to add a VBAT label, same label that I used here in the little battery charger integrated circuit. So I'm just going to copy that, duplicate it, and connect it there. And the other one, of course, is going to be the ground level. Done. So let's put that in the box and give it a name. Next up, I want an indicator for power. So I'm going to grab a copy of the red LED and its current limiting resistor. I'm just going to duplicate these two, rotate like that, and place it, say, around here. And the idea here is that when there is power, then 3.3 volts is going to come out of the regulator into this LED, and then, of course, into ground, and the LED will let us know that power has been applied to the circuit. Add a label here, even though this is not really necessary, but power LED, I'm just going to give it a named net so I can see this particular net in the layout easier later on. So done with that. First page is pretty much done. The only next thing that I want to do is to add a hierarchical sheet symbol so that I can then connect this sheet to the next one up in the hierarchy. So I'll select this tool, click on it, and then just draw a little box here. Oops, do that again. Yep. Like that. I'm going to give this sheet a name, and what this sheet is going to contain is the ESP32 and related hardware. So I'm just going to put in here ESP32 C302. This is the main component that's going to be in that sheet, and I'm going to change the name for the sheet file as well, ESP32 C302. So I'll be able to see that file in the file system in a moment, and I know what it is about. So save, then have a look. You can see I go back one level. I've got my new sheet just right there along the rest of the sheets that make up the project. Hit escape a couple of times to exit the tool. So now I've got the second sheet. You can see that it also appeared here. The second sheet is blank. Before I go over to work on the ESP32 sheet, I just noticed a couple of things that I need to fix that has to do with the LEDs and the colors of the LEDs and the pins to which each of these is connected to. And I also want to introduce a couple of labels as well, just to make it easier to see and understand the role of each of these wires when I'm working on the layout editor. First thing to do is I just noticed that this red LED is connected to STAT2. STAT2 is the pin that indicates charging. However, I want the red LED to indicate that charging power is good. I can either do that by rearranging those wires or just moving the LEDs around. Actually, that's what I'll do. I'm just going to remove those wires to release the LEDs and move those around. So I want the blue LED to be connected to STAT2, and STAT2 indicates the charging of the battery. So blue LED means charging. The green LED indicates charged and it's connected to STAT1, so that is fine as it is. I should not have removed those wires. So let's place that here and rewire everything. Now the other thing that I want to do, as I said earlier, is to use labels to mark the functionality of these wires, and that makes it easier later on in the layout to know what wire I'm dealing with. So this one is going to be charging power good. I'm just going to double click because a G is missing. All right. The second one is going to be charged. And the last one is going to be charging. So that's done as well. And I've got one more label that is missing. This one here, actually, just noticed this should be 5 volts. I'm just going to copy that and duplicate it. And that is going to be a 5 volt label. And I just noticed one more thing. I don't have a value for R6. So let's do that now. So R6 should be 20K. I'm pretty confident that this is correct now. I haven't forgotten anything. So we can continue now with the second sheet. Let's continue with the second sheet, which will contain the various circuitry relating to the ESP32 and things such as the USB module, flash memory, and the SD card module. I'll put all those in the second sheet. So you can get to the second sheet either by clicking here in the schematic hierarchy, just the second sheet. You can reveal that window by clicking on this button here in the left toolbar, hierarchy navigator. Or you can double click on the hierarchy symbol in the first sheet. Just double click and it will get you there. And another thing that you can do that I always like to do is to go into the symbols property and just change the fill color so that it's a little bit easier to see. I'm just going to make it something like this with a bit of opacity. So kind of look a little bit like this, a bit more interesting and striking. Later on, you'll see that I'm going to attach labels to this box in order to enable communications between the two sheets. So let's go ahead, second sheet, and just like before, I'm going to start by dropping the major components onto the sheet. And to make it a little bit easier for us to know what those components are, I've gone to the BOM and I have highlighted with yellow the main components that are part of this sheet. So we have the memory card connector, that's the SD card connector, the ESP32 chip, the CP2102, which is a USB to UART bridge. I've got another chip that acts as an ESD suppressor that will be working alongside the USB to UART bridge. I'll talk a little bit more about this in a moment. And finally, the flash memory chip. Let's start with the USB module. I'll hit the A key and I'll search for GSD0900, and there it is. I'll place that somewhere here. I'll continue just so you can see what I'm doing. I'll continue with the next item in my list, which is the ESP32 U3 component. So I'm just going to search for that. C3. The one that I want is this one. Okay, and drop that there. Next up in my list, I've got the USB to UART bridge, CP2102. And I'm looking for the GQFN20 package. So I'd go 20, this one here. Place that here. One more is the flash memory. So that is this item down here. Actually, sorry, I skipped one. U5, that's the ESD suppressor. So let's look for that first. I've got a few options there. The one that I want is this one right there. The differences have to do with the packaging, not with the schematic itself. You can see the first two have got 6 pins out. It's just the packaging is slightly different. So the one that I'm going to go for is the 2SC6. And then finally, I've got the U6 component, which is the flash SPI flash chip. So that's W25Q. This one here. There's a few options, but that's the one that I'm looking for. Double click and I'll place it, say, here. Before I continue, I'm going to review the designators for the components just to make sure that they match with the ones that I'm using in my notes, because if I don't, there's a high chance that I'm going to make mistakes later on. So the ESD suppressor chip, I'm going to rename that to U5. The USB to serial bridge, that is going to be U4. The ESP32 chip is going to be U3. The SD card module is J3, that's correct. And then finally the flash memory, that is going to be U6. I suggest you do that as well if you want to keep track of what I'm doing, because I'll be referring to these components by their designators. And all I'm trying to do here is to make sure that the notes and the designators in my notes for the various components match with what I have in the actual schematic. So that's all I'm doing here. Now let's talk a little bit about these components. This integrated circuit U4 is a USB to UART bridge, and it enables communications between a computer and the ESP32 C3 module via a USB connection. So it converts USB signals to serial UART signals, making it possible to program and debug the ESP32 C3 directly from the computer while handling USB power delivery to the board. So that's the purpose of this chip. Now, alongside this chip is a smaller chip, this U5 USB LC6, and this is a ESD suppressor chip. This chip here protects the bridge, the USB serial bridge, from electrostatic discharge events, which can occur during handling or when plugging in USB connections. So it clamps high voltage spikes to safe levels, preventing damage to the chip while maintaining signal integrity for reliable data communication. So I'm also going to follow the information in the data sheets for all of the wiring that you're about to see. So for example, I've got the documentation for the ESP32 chip. I showed you some of this a little earlier. Actually, a better place to look for that information is the development kit schematic diagram. So for example, here you can see how Espressif themselves have wired the ESP32 module to power and to ground. And I'll be following this example as well. In particular, I'll be implementing the reset and boot button functionality following this exact schematic. So that's one place to look for. Another thing to show you is the CP2102 chip. This is the USB to serial bridge, and there's a lot of information here on how to do the wiring. I'm not going to go through it because it's a lot of detail. It would take a while. But if you are interested in learning the details and understanding why I did what I did the way I did it, have a look at these data sheets as well. Here's a data sheet for the SD card module. This is mostly mechanical. There's not much else going on. So I looked at this just to get a better understanding of the mechanical attributes of this connector. And finally, I've got here the data sheet for the flash memory. This is an SPI interface flash memory. It doesn't have specific information on how to do the wiring, but I'm using conventions for wiring integrated circuits that communicate with a host using high data rates and high frequencies. Let's begin. I'm going to start with the top left side of my schematic and work my way to the other components. So since I've got the ESD protective circuit, I'm just going to move these 2 bits to the side for the time being at least. Okay, I'm just going to reorient this component to make wiring easier. Pin 2 goes to ground. I'm just going to grab a ground pin from here. Place that there. So that's going to be ground. I'm going to leave pin 5 alone for a second because I need a couple of resistors for that as a voltage ladder. Next, 3 is going to flip this component across. So select it and just click on this button up here to mirror vertically because I want pin 3 to be up on the top side. Just makes wiring easier. So pin 3 will go to pin 4 on the USB to serial bridge, and pin 1 will go to 5. Pins 4 and 6 need to be connected to pins in the root page. So to do that, I'm going to use this button here to create hierarchical labels. So the first label is USB DN. So USB DN and for negative. I do have flexibility on to where to connect it, but I'm going to connect that to 6, to pin 6 to begin with. And I'm going to create a duplicate of this label. Double click on the duplicate and change this N to P for the positive side of this differential pair. So I've got USB DP connected to pin 4 and USB DN connected to pin 6. Now in the root page, I'm going to use the Place Sheet Pins tool to expose the 2 sheet labels that I just created in the root. So click on that, click here, and you can see as I'm clicking and then click again to commit, bring across the 2 labels, the 2 hierarchical labels that are created in the second sheet. So these 2 are now exposed to the first sheet right here. And I can actually finish the connection of those 2 sheets by connecting. You can see there's pins here that I can connect to something else. So I'm going to grab the 2 labels that I've already created, these 2, create a duplicate and bring them down here to finish the connection. So I've got the DN that needs to go right there. I'm just going to use wires for that. And DP that goes there. Use wires to finish the connection. The 2 pages now, the 2 sheets are now able to communicate. Let's go back to the second sheet and I'm going to finish this work for this particular component by adding the 2 resistors to form a resistor ladder. So there's the first one, just R. There's one here and another one here. It's going to be R12. And the value for R12 is 22.1 K, or I'm going to call it 22K1. The second one, its designator is 13, and its value 47.5 kilo ohms. These 2 form a voltage ladder for VBus, like this. Just move that down a bit. And then the other side of R13 goes to ground. Like that. On the top side, we've got VBus. So VBus, of course, is coming into this sheet from the root sheet. So I'm going to create one more hierarchical label called VBus and connect that here and go back to the root and expose it. Like that. And from here, I need to find a VBus label to bring across. Done. Back to the second sheet. One thing to notice is that these labels have got shapes. So depending on what shape you use, you can see that the shape of the label itself changes as well. These are really just visual, so I'm going to keep them as inputs here. And the VBus is also an input. Next, I'm going to take a wire from pin 5 and connect it to VBus. So that's how this chip is being powered. Or if you don't like the label, you can just use the bus. I'll do that actually just to minimize the number of wires that I'm using. All right. Now while I'm at it, I'm going to create a few local and named nets. So the first one is going to be USB data plus. So I'm going to connect that to the P right there. And the other one is going to be minus. Again, this is going to be a differential pair. So I'm using plus and minus so that later on when I go to the layout editor and I start doing the drawing of the traces, KiCad will be able to tell that these two wires belong to the same differential pair because they've got the minus and the plus signs in their net names. Now, as per the specifications for this device in the datasheet, I also need a capacitor. Just a regular capacitor will do. I'm going to place it here, connect the other side to ground, just move that a bit further down like this, and that goes up here. And this capacitor is going to be C11, and its value is going to be 1 microfarad. And let's continue. I'm going to have one more ground down here, and up on the top side, actually I need to move everything down a bit because I have a few components to connect up on the top side. So I'm going to start with a resistor, oriented like this. This resistor will be R11, and it's going to be 1K. That will be connected between the reset pin and pin 7, which is the voltage regulation in. And I'm going to connect VDD in there as well to the same pin. Then I've got two bypass capacitors. One of them is going to be a regular capacitor, and the other one is going to be electrolytic or polarized, oriented like that. Let's set the values. So the one in the bottom is going to be C10, and its value 0.1 microfarads. And the polarized one is going to be C9, and its value is 4.7 U. It goes there. And then these two go to ground. Like that. And on the top side, I'm going to have a 3.3 volt symbol. So that side is done. On the right side, I'm just going to mark a few pins that I won't be using first. Do not connect that and that. And the suspend pins we don't need. Wake up either. After that, I want to have two LEDs to indicate traffic. So you can see TXT and RTX. So I'll connect two pins here to show when there is traffic. So I'm going to copy this block of components, blue and a red LED, along with the resistors. So Command C, go back to the working sheet and paste those here. This saves time. Just orient like that. So I'm going to put the green LED actually on the top side. Again, this is totally arbitrary, of course. But in order to do myself the courtesy of not making a mistake and diverging from my nodes, I'm just making sure that what I'm drawing here reflects what I have in my nodes. All right, and these two then will go to the 3.3 volt. So I'm just going to copy this symbol and place it right here. Here I've got TXT, RXT, and the RTS and CTS, and instead of wiring them using actual wires, I'm just going to use labels here. So this one, the first one is going to be TX RX, and that goes here. And the second one, duplicate, is going to be RX TX. It goes there. Next, RTS. And finally we have, I'll call this one DTS. Okay, I think this is complete. So I'm going to put this in a box, move it down a little, and give it a name. This is the USB module. Okay, looks okay. I'm going to have another look at it later on before I commit. Let's work on the ESP32 module. So I'm going to place around here because I'm going to have more components on the right side. I just noticed that this resistor should be 18, R18. So let's begin here. I'm going to start by dropping a new resistor. Place it here next to IO6. And this is a small 50 ohm resistor. All right, so that goes to IO6. And on the other side, we'll connect the two SCLK net. After that, I've got several net labels to create and attach to these pins right here and down the bottom right there. So start with the ones that I've already created, so I can just duplicate them. So first I'm just going to copy these two, create duplicates, and move them over to this side and rotate and just connect them to pins 12 and 11, and that's good. Next up, I've got a bunch of net labels to create, so I'm going to use the L key for that. So the first one for up here, pin 2, and this is going to be EN for enable. Done. Next one, it's going to be CS_SD. That's going to go to IO0. So the roles for all those pins, just by the way, if you are a little bit confused right now, we'll find all that information in the datasheet right here. So there is a table here, right here, that tells you about the roles of each one of the pins so that you know what label to create in order to connect that pin to a particular net. So next up is IO1, which is going to be connected to the sensor. I've connected that to the photo sensor. So this is a general purpose pin. You can do whatever you want with it, of course, but I've decided to connect this particular one to the photo sensor. Next, I've got the SPI interface. So I'll create a new label called MISO DO for data output, and that goes to IO2. Then there is SCL, so the I2C interface, and SDA. And for IO5, there's another general purpose input-output, and I've connected it to the microphone. So I'm using the mic out net to convey signal from the microphone or from the sound sensor. So the left side is done. Let's go over to the other side now. I'll continue with some more labels since I've started that process. There's going to be GPIO19. So that goes there. I'm going to connect this particular net to one of the headers. That's GPIO18. Next one up is going to be CS or chip select for the SPI interface. And that's going to be boot and GPIO8. This one is going to be connected to the boot button, just like this one here goes to the enable button. 3 pins remaining. I'm going to duplicate the ground symbol so that I can connect it to the ground pin right there. Then I've got IO7. For IO7, I need a resistor. So add a resistor, oriented like this. So this resistor is 50 ohms and it goes to MOSI. So there's another label. It's data input for the SPI interface. This is going to be R15. So it's R15 and I need to correct this one here. This is R20. And finally, the power for this ESP32 module. As per the specifications, I'm going to connect this power to 3.3 volts, but I also need a couple of capacitors for bypass and for just signal conditioning. So I'm going to have two capacitors there, one polarized and one unpolarized or ceramic. So there's the ceramic one, and let's put one more polarized. I'll place that there like this. I'm just going to switch the names. So C7 should really be C8 to remain consistent with my notes. That's going to be 0.1 U or 0.1 microfarads. Okay. And the other one is going to be C7 and its value is 10 microfarads. Connect these to ground, and on the top side, just going to use the W key to start drawing. Just going to draw it like that. Actually, I think it makes more sense if I draw it like this. Yeah, I'm going to move all this down a bit because just to reduce the number of angles that appear. So like this, G key, just to make it look a little nicer. I think this is good as it is. Put a box around it and give it a name. Done. Let's continue with the SD card module. So this is a SPI device, so it communicates with the ESP32 using SPI. So I'll start with connecting the SPI, and then there's a couple of capacitors and resistors as well for signal conditioning. I'm going to grab the MOSI and MISO and clock. There's clock. And the select, I just noticed a mistake actually, I'll unclick everything. This is the select signal for the SD card. So it should be SC for select, SD for SD card. All right, so let's try again. So that, clock, and that, I'll duplicate them and bring them all around here so I can attach them to the SD card reader module. So MOSI goes on this side here. Clock goes here. The chip select goes here, but I will need to add a resistor. This is just a pull-up resistor. I'll just place it here and set it up. So this is R19, and the value of this resistor is 10K. And as I said, this is a pull-up resistor, so I'll just draw it like this, pulls up to 3.3 volts. I can just make this a little bit more economical with space and just connect it straight like that. G to make it look better. Okay, and then finally I've got the MISO, and that eventually goes here. Just gonna move this out of the way for a moment. Okay, that goes to that 0 pin, but I need a resistor, a small resistor, again, signal conditioning right there. That is going to be R16 and just 50 ohms. Make sure, because I hit escape, so it didn't commit. So R16, 50 ohms, and that goes there. Done. Just move these two out a bit using the G key. DAT1 and DAT2, along with the pins down here, all go to ground. So I'm just going to get a ground component, place it there, rearrange a few things. Actually, I don't really need this long wire. I'm just going to move this symbol down a bit, rotate, and connect straight like that. All right, next I've got DAT1 goes to ground, DAT2 goes to ground. Move these two labels up there. And also I've got, actually I'll be economical with space and wires. I'm just going to do one more ground there, and all these go to ground. Then I'm going to mark these pins on the left as do not connect, and then I've got one pin remaining, which is the power input for this module. So for that, I need a couple of capacitors, just like with the other examples earlier. And it so happens that these capacitors have the same values as those are used up here in the ESP32. So I'm just going to copy those or duplicate. And I've got SID12 is meant to be the electrolytic. So I'm just going to change the designations. So this is going to be 12 at 10 microfarads. And this is going to be 13 at 0.1. And that goes right there. And finally, I've got a 3.3 volt to power the module. I'll bring the grounds down here so they're kind of at the same level. It looks a bit better. And that is it with the module for the SD card. Put it in a box, give it a name. One more thing to mention here is that the DAT2 pin on the micro SD card is typically used in 4-bit SD mode as one of the 4 data lines. So you've got data line 0, 1, 2, and 3, 4 data lines in total. However, in SPI mode, which is commonly used in microcontroller applications like the ones that we are building here, the DAT2 pin is not required and it can be left floating or better connected to ground, which is what we're doing here. So in SPI mode, which is the mode that we are again using here, only the following pins are actively used. We've got DAT0, so you see I've connected that to MISO data out, CMD, which is connected to MISO data in, clock right here, and CS right here, the chip select, and then again DAT2 and DAT1 are not used in SPI mode. One more thing to do, and that's to connect and wire up the flash memory. So the flash memory is also using the SPI interface. So I'm going to duplicate some of the relevant pins. So these 4, I'm going to move them over here. There is one more for the chip select. I'm using this one here. Duplicate that and move it over across to the side. Let's do the wiring. So CS goes here. Clock goes here. MOSI goes here. Data input, DI. MISO, data output goes there. DO, okay, data output. Actually, I need to do conditioning here, so let's just remove that out of the way. And I need another small resistor. Just going to copy the one from here. This one, duplicate it, and move it over this side. So this is 50 ohms. And this should be R22. Actually, I'll move all that a little bit to the left because I need to do something with pin number 3 right there. So pin 3 along with hold will go to 3.3 volts. So we're going to be holding those at a high level. So that goes there and that goes there. Better. And on the other side, I need just a single capacitor. So bypass capacitor to connect ground to ground. And on the other side, VCC will go to 3.3 volts. It's going to be C14 and 0.1 microfarads is sufficient. So move that a bit closer and we're done. All right, let's put this in a box. And this is going to be the flash memory. Almost done with this page. From this page that contains the ESP32, we are going to branch out to 2 other pages. One is going to contain the hardware for the sensors and the other one for the user interface. So just like earlier, I'm going to create the hierarchical sheets for those 2 additional pages. And I'll start with the sheet for the sensors. I'll call that sensors, and the sheet file will be sensors, and I'll give it a color. Let's make it cyan. And the second one is going to be for the user interface. So that's user interface. And for the sheet name, I'll just say user interface. And I'll use fill color. I'm going to make that orange. Okay, let's try again with the sensors. Let's go to the properties. I clicked on the border instead of the fill. Cyan. All right, that's better. Okay, so we're going to add bits and pieces in those boxes later when we start work on the sensors and the user interface. So save. Just going to do one last cross-check before I leave this sheet alone for now. Oh yeah, one thing that I haven't done was to fill the data in the legend down here. So let's do that. So this is going to be ESP32, C3, USB, and flash memory. Okay, that's good. Save. Just going to take a moment to check everything. Here's one thing that I forget. I'm just going to do it now before we continue. What I want to do is to have a few test points in the final PCB. So these are pads on the board that I'll be able to attach test instruments just to check on the operation of the board without having to tap onto pins. So I'm going to add a few test points here. To do that, I'm going to move these two blocks a bit to the right, just to make a bit of room. And I'm going to add the test points right here. So tap the A key, search for test points. You can see there's a test point here. I'm going to go for the just simple test point. It looks like this. Orient them like this or like this. Doesn't really matter. So this first one is going to be mossy. Just going to duplicate them. I want to have 5 of those. I want to be able to test the SPI interface. So 1, 2, 3, 4, one more, 5. So I want to have mossy, meso, clock, and the 2 select pins. Duplicate those. Just put them up here for now. So the first test point is going to be mossy. Place that right there. Second one is going to be meso. Then I'll have the clock. And then I'll have the chip select signals. So for the SD card and for the flash memory. I changed the name. So this is going to be test. I use lowercase. Test mossy. Test meso. Test SLK or clock. Test CS SD. And finally, test CS. Give them a bit of space. Before I move to the next sheet, just notice one thing here. I'd really like to have this capacitor on the left side so that it's closer to VDD. So the way to do this really quickly and easily is to just select the 2 and then use this button up here, mirror horizontally, or just type X and it will flip it across. And I use G, just move the bundle of components together to the one side. Do the same thing again down here so that everything is nice and symmetrical. So I'm going to save and then continue with the next sheet, which is the sensors sheet. Let's continue with the next sheet in line, which is the sensors sheet. So in here, I am going to create a circuitry for these main components. The microphone preamplifier, the BME 280 environment sensor, there's the ambient light sensor, and the microphone. I've already collected, of course, the datasheets for these components. You can see here is a datasheet for the microphone preamplifier, fairly straightforward. I'll be implementing this circuitry right here. Here is the ambient light sensor, fairly straightforward to implement. The microphone that works with the preamplifier, and the datasheet for the BME 280, also fairly straightforward to implement. There's nothing to it. Really, it uses the I2C interface, and we can just follow the general guidelines for any I2C interface device to connect it. As always, I'm going to start by dropping the main components onto my designer. There's the BME 280. Start with that. Next, I'll add the microphone and the preamplifier. CMC50, that's the one. that I downloaded from Snapita a bit earlier. So that goes there. And I also need to get the preamplifier, which is model number MAX 4466EXK, that one right there. So place that right here. And then there's also the photo sensor. So I'll put that up the top. So there's going to be TEMT right there. I'm just making use of my previous research here so that I can search by the various model numbers or other keywords. Obviously, I don't remember those things by heart. I'm going to start with the BME 280 and set up the supporting circuitry. It's pretty simple. So this is just an I2C device. So I only need a couple of resistors for the pull-up for the two lines, for the clock and for the data line. So add a resistor. Here, this is going to be a 4.7 kilo ohms resistor, 4.7K or better 4K7. And I'm going to call this R24. And I need two of those because I've got two lines that I need to pull up. So there's going to be the same value, but there's going to be R25. Okay, done. And I'm going to get a 3.3 volt symbol, which I have used recently. I'm just going to place that there. Move these down a bit. So CSB will go to 3.3 volts. Just going to move that here. So that CSB will connect straight to that level. And then I'll have the two resistors to also connect there. And the other side of the resistors, one will go to SCK. I'm extending a little bit because I'm going to connect the net to that extended wire in a moment. And then there's SDI. I'm going to extend for the same reason. Done. And then I will have two hierarchical labels. One is going to be SCL right there, and the other one is going to be SDA. Just going to improve the layout a bit, move that up a bit using the G key to move, and see if I can get those two wires up a little more. Yeah, of course, fix all this. There's no connection there. As much as possible, I try to prevent having too many angles. That can move in a little more, like that. Now SDO will go to ground. So what I'm implementing here is an address. So with SDO being grounded, the address for this device is 076 hexadecimal. On the other side, I'll have again the 3.3 volt symbol, and I'll connect both VDDIO and VDD to the same level. Then I'll have a capacitor, just a simple ceramic capacitor. This is C15 and its value 0.1 U. And that will go to ground, like that. And that implements the BME 280. So I'll put a box around it. That's done. Let's continue with the ambient light sensor. This is just an analog device, so all we need here is a resistor to pull it up. So this is going to be R23. Let's make it 10K. And that gets pulled up to 3.3 volts, since that is our supply voltage. That goes there. And then we also need a hierarchical label that will connect the output of this circuit to photo C. That is the net that we will connect to one of the pins in the ESP32. And of course, on the other side, we've got ground. One thing I'll do here is I'm going to change the symbol of this sheet label to be an output. Let's put a box around this block. Next is the microphone and the preamplifier. There's a little bit more circuitry involved here. Start with the preamplifier. On the other side, on the right side, I'll have the power supply. So it goes straight there. I need a small capacitor, so it's the same value as C15, so I'm just going to duplicate that. It's going to be C18. One side is connected to 3.3 volts, the other side to ground. Let's grab a ground, place it right here, like that. Now here's the output. So for the output, I'll take a hierarchical label. It's going to be mic out, and that is also an output. So that will go there. Connect these two, like that. And I need a feedback line to go back into in1, right? So from here, just going to type the W key to start drawing and got towards the back. I'm going to stop here because I need to include a resistor for line conditioning. So here's a resistor. That's 100K, and that's R31. So from out, that signal goes into the resistor, and from there it goes to the input. There's also a capacitor here. Place that there. That's C20. And its value is again 0.1, so that's fine as it is. And connect it to the signal. Then from in, I need one more resistor, which is going to be R29 with a value of 1 mega ohm. That goes between that and ground. No, sorry, this one is R30, and it's not 1 mega ohm, it's 10 kilo ohms. It's a pull down resistor. I do have a huge 1 mega ohm resistor coming up for a voltage divider. Move that a bit to the left and continue with the positive in. So I need 2 resistors for that. I'm just going to copy one of them here. So this is going to be R29, and that is 1 mega ohm. It's part of a voltage divider, and it goes to ground. And on the other side is R27, which is also 1 mega ohm. And it comes out of in1, like that. I'm just going to move both of them up a little, like that. Just using, again, the G key to move things around without breaking connections. Now from here, in the middle of that divider, I'll connect the output of the microphone, and of course the ground goes to ground. On the top side of that voltage divider, connect the 3.3 volt power. There's one more voltage divider. Just going to copy this resistor a couple of times. The first one is 2K and R26, and the second one is also 2K, so I'm just going to duplicate R26. This is 28, yep, correct. Connect that here. That comes out of the output from the microphone. So move the microphone symbol to the left. Move that a bit closer and connect the output to the bottom of the voltage ladder. The top one goes to 3.3 volts. So I'm just going to move that here and connect it like that. And then on the left side of the voltage ladder, I've got one more capacitor that looks like this, and it is C16, and the capacitance is correct. And from there, connect one side to the middle of the voltage divider, and the other side will go to ground. And I think that the circuit for the microphone and its amplifier is also correct. So I'm going to put it in a box. So now I need to connect the two sheets. So the sensors sheet, you can see there's a few hierarchical labels. There's 1, 2, 3, and 4. So now I need to bring those hierarchical labels from the sensors page to the ESP32 page. So here is the box that connects it together. And I'm going to use this button here, place sheet pins, to bring those labels across. So the first one is here. I just do that, click again, bring the next one, click again, bring the next one, and click again, bring the next one. And that's it, we're done. So let's go back and finish up with the connections. Go to the ESP32 and grab SDA, SCL, photo C, and mic out. Duplicate, bring them across, rotate, and then just connect them with a small wire each one. So here's SDA. I can connect them straight away like this, but I just prefer to have a small wire in between just to separate the box from the text. So SCL, photo, and mic. Done. Let's save and let's continue with the last sheet, which is the user interface. Let's work on the remaining sheet, which is the user interface. So double click on the user interface. And let's begin with the components. In yellow background, I've got the main components for this sheet. There's J4 and J6. Just notice there's no J5, and that is okay. So the J4, J6, the two connectors. I've got two transistors for the boot and enable buttons, and there's two buttons there as well, switch 1 and switch 2. And there's a few other smaller components like resistors. Let's get started. I'm going to add the two connectors first. The first connector, let's make it con. We need a connector for the display, which uses the I2C interface, and therefore it requires 4 pins. So there's going to be one row with 4 pins. I've got an option here of what kind of connector to use. I'm going to just go with a simple straight connector. So this one here, and I can always change later. So there's the first connector. For the second breakout, which is the one that I use to just break out any remaining pins, I'm going to need in total 5 pins. So there's 3 GPIOs that I want to break out, plus power and ground. So let's do that. I'm going to do something similar, but instead of 04, I'm going to look for 05, and I'm just going to use the pin connector just for symmetry and simplicity. So this one up here is going to be for the OLED display if you'd like to connect to it. Otherwise, you just have a breakout for the I2C interface, and this is for the GPIOs. On the right side, I'm going to break out a couple of buttons first. Let's see, I think I've imported USLPT buttons. Yeah, 2 of those. So I need 2 of those, 1 and 2. So one is going to be boot, and the other one is going to be enable. Switch 1, switch 2. And then I also need the 2 transistors. And for this particular job, I'm using the BC817 NPN transistors. This is using the SOT or SOT23 package. And Q3 right there. I'm going to work on the connectors first because they are really easy. I just need to add a few labels and they're done. And then we'll go to the reset and boot buttons. So for the OLED display, I'll start with power. So 3.3 volts. I'd like to have this around the other side. So just move to the side so that the pins can be connected on the left. I also want to flip it over. So I'm just going to flip. There you go. Flip that over so that number 1 pin is on top. Because I'd like, just for the sake of consistency, I'd like pin number 1 to be power. In this case, like that. And it's just that ground for pin 4. And then I'll have SDA and SCL. I'm just checking to make sure that the configuration of the pins as to which one is SDA and which one is SCL matches my actual LED display. Let's grab a hierarchical pin, or hierarchical label I should say, and this one is SDA. It actually should be bidirectional. So let's change that to bidirectional. It goes there. This is SCL, also bidirectional. I'm just going to put a box. You can always use it to connect a second I2C device or more if you want. It doesn't have to be connected to an OLED display. Let's continue with J5. So I'm going to do the same thing, flip it across and then vertically as well. So the number one is on top. I'm going to duplicate these two and connect number one pin to 3.3 volts, number 5 to ground, and the rest are going to be GPIOs. I'll use the H key. The first one is going to be GPIO 8, bidirectional. I'm just going to copy this a couple of times to save a bit of time. Duplicate, I should say. Second one is going to be GPIO 18, and the third one GPIO 19. And finish with the connections. Okay, that's done. Then let's go to the main part of this schematic. I've got the two switches, and down here I'm going to create a circuit to manage the signals for boot and enable. What you're looking at here is a schematic from ESP32 for the ESP32 S3 Dev Kit 1. What I'm going to do is just to implement the circuit down here that manages the boot up process of the ESP32. If you want to learn more about this, have a look at this documentation page on the ESP32 website that explains how the boot operation and the bootloader mode works in the ESP32. I've got a link to this document in the description below. So I'm simply going to essentially copy this schematic here. Let's start with the two transistors. I've got Q2 and Q3 here. I'm going to start with a bit that I always get wrong because I've got to cross some wires. First, I need a couple of resistors for the base. Place that there. They're both 10 kilo ohms. Actually, one thing that I should have been doing since the beginning of this work here is instead of doing what I'm used to be doing and double clicking on a symbol to bring up its properties, I can simply look at the properties on this sidebar here. Just click on this button to reveal the properties for whichever symbol you have selected. So you don't really need to double click anymore and go into the properties window. You can do most of what you need to do in the properties window that appears on the side. Here's the fields, reference, and the value. So I'm just going to add it directly in here. This is going to be R33 and the value is 10 kilo ohms. And I'll duplicate that resistor, place it here, and get the name right here. This should be R34, which it is, and 10Ks. Next, connect the resistors to the base and continue with the drawing of the wires for the two transistors. It goes like this. Just going to move that out a bit so it's not too close. So that's one thing. Then I need a couple of hierarchical sheet labels. One here. This is going to be DTR right there, and that gets connected like this. And the second one is going to be RTS. That gets connected here. I should move that further down actually, now that I think of it. All right. Now there's two more hierarchical labels that I need to add. The first one is EN, and that is an input. That goes there. I can just connect it right there. And the second one is boot, and that is also an input. And it goes in like that. I'll just be more specific. These are going to be outputs. And same thing with this one. So signal comes from the buttons as an input to the transistors and then provides an output to the ESP32. All right, so that goes there. We're good with that. Let's continue with the buttons now. I've got the button signal coming into the button S1 like this. And I'm going to put a dip bouncing capacitor in there as well. See, like that. This is going to be C21 and its value is 0.1. A bit closer, connect to the boot signal, and the other side would go to ground. So let's grab a ground symbol. So it goes there. From the other side, pin 4 of the button goes back and gets connected to pin 3. Pin 1 and pin 2 together get connected to ground. I'm not sure if I like this line going over the component, or I can simply have ground on the other side, but it's aesthetic. I'm just going to leave it like this. So this is the boot button. I'm just going to use a bit of text here to mark it as such. This is boot. Another thing you can do here is to select this button, and for the reference, or actually for the value better, replace that text with the text boot. And I'll just delete that label. All right, same thing for S2. I'm just going to replace that with this actual role. This is reset. So let's set it up. Just add a bit of space between the two buttons. Well, the first thing to do is to add a pull-up resistor on pin 3. So I'm just going to duplicate R33 and flip it over like this. The only thing I'm going to change is its reference designator to 32. The value is correct as it is. And connect it to 3. Then I'm going to duplicate the label EN and connect it to pin 3. Going to add a ground on the other side so that pins 1 and 2 are connected to ground, and then another capacitor. This is correctly C22, but as per the specifications, the capacitance should be 1 microfarad, and that goes here. And pin number 4 also gets connected to the capacitor. Get another ground and connect it to the other side of the capacitor. Now, one thing that I'll add here is an image of the truth table that we have implemented here with the 2 transistors. Move that down a little. And there's a button here that allows me to import images. So click on that button. I've taken a snapshot of this truth table a bit earlier, saved it as a PNG image. So go to the project folder. Actually, I think I put it in libraries. Data sheets. Yeah, I'll put it in here, and here it is. And there's the truth table. It's just an easy reminder for me to remember where this information came from. You can even add a bit of additional text using this text box. Something such as, to learn more about the ESP32 boot mode, go to, and I've got a short link here, to explore /ESP32 boot. And that looks like this. And I think it's handy to add content like this in order to make it easier for you to communicate with anyone else who might be looking at your schematic. And I'm going to actually do that as well. Once I finish with all the drawing, I will add some annotations just to make it easier for anyone who's looking at this schematic to understand what's going on. One thing that's missing here is, of course, 3.3 volts for the pull-up resistor. Let's grab that, paste that here. Okay, anything else? No, I think it's okay. So I just need to link the sheet now with ESP32 page 2, and I think we'll be done. Let's go back here. As you can see, the user interface box is empty right now. I'm going to grab this tool and start adding the pins that are missing, like that. That's better. I also think that this color is probably a bit destructive, so I'm just going to make it a little lighter. reduce the opacity. Let's finish up with the connections. So SEL, SDA, EN, boot, GPIOs, 3 GPIOs. Just duplicate those for now and bring them down here. And there's also the RTS and DTS. And then it's just a simple matter of attaching them to the correct place. So RTS goes here. Okay, so I've just noticed a mistake here. This is DTR, where this is DTS. The correct name for this particular pin is DTR. So let's fix that. This is going to be DTR. And I'm just going to search for DTS. Bring up the search panel down here. Search for DTS in labels. And you can see that there is one right here. So I'm going to change that to DTR. And of course, I could have done that on this side panel right here as well. Continue little fixes here and there as required. So connect DTR hierarchical sheet label to the local label. Then go for GPIO 8, GPIO 18, GPIO 19. On the other side, I've got boot, so I rotate that, enable, and then SEL and SDA. I'll copy those or move those together. Done. All right, so this work is complete on the schematic. I'm going to add some annotations, but I'm going to do that offline. And before we move on to the next step, which is to work in the layout, I'm going to show you the annotations and the final schematic before I continue. So thanks for following so far, and we'll continue in just a few seconds. I've completed the schematic, but there's a couple of things that I need to do before moving on to the layout editor. The first thing is to do the associations between symbols and footprints. So the symbols are everything that you see here in the schematic editor, and footprints are the representations, the physical representations of these symbols that I'll be using in the layout editor. The second thing is to do the validation and error checking. I'll be using the Schematic editor's electrical rules checker to do that. So let's continue with the symbol and footprint associations. There's a specialized tool for that, which is this one right here, assign footprints. So let's have a look at what we have. So, okay, just say okay to these legacy entries notifications. So some components already have associations. You can see here that F1 has an association. It's the fuse. The connector J1 also has an association, and so on. But many other components, like these capacitors, for example, don't have an association. So let's go ahead and add those now. For passive components like the capacitors, and there's a bunch of resistors down here as well, I am standardizing those components for the 0805 SMD versions of these resistors. There's many different sizes, of course, and I can go for through-hole components, and I can go for tiny SMD components as well. For this particular design, where I am trying to balance the size and the cost, I'm going to go for a more general purpose size, such as the 0805. I could go much smaller than that, but that would increase the assembly and manufacturing cost. I'm going to start with the first one. And actually, what you can do in KiCad, you can even select all of them. Actually, I'll do that because all of those are the same. I think there are a couple of footprints here that I'll be using tantalum capacitors, such as this one right here, the C3. Hold on a second. Yeah, C3 here and C4. Those are going to be tantalum capacitors, so I'm going to leave this aside for this multi-select. I'm going to go for all the small ones. I'm selecting them all using the Shift key and my mouse, and then using the Command key or Control in Windows, I will unselect all those capacitors that I will be assigning to tantalum components. So the 10Us, also the 4.7Us, I'll exclude those two. And I'm just looking at my notes now. I believe, yeah, everything else is okay to go with a 0805 2012 metric footprint. All right, so having those selected, then I'm going to go to the footprint libraries on the left side, and look for capacitor SMD. And on the other side, you can see my filters here as well are such that when I click on a library on the left side, only the components that are part of that library appear on the right side. If I unselect this filter, you can see that the options available multiply because everything now is available. So play around with those filters so that you can reduce the number of items that are showing in the right side, just to make it easier to find what you're looking for. It's just a little annoying though, that it's just not very easy to see when a filter is selected. There is a faint blue border around it to indicate that it is selected. Okay, so now I'm looking for 08 or 5. You can see there's much smaller ones like 02 or 1 and so on. So I've selected the capacitors that I want to apply the association, and I've selected the footprint that I want to associate these capacitors with, the 08, 05, 2012 metric. And I'm just going to double click, and you can see that they've been assigned. You can also, I'm not going to do it now because my release candidate 1 version of my KiCad 9 instance crashes when I do that. But if you want to see exactly what you're assigning to, you can select the footprint and then click on this button right here to view the selected footprint, and that will actually bring it up in a small editor window. Let's now do a multi-select for the tantalum capacitors, and for this I'm going to go into capacitor tantalum SMD. I'm going to search using the filter here because I have installed a specific capacitor footprint that I found, and that's the T491A, and I believe that the capacitor is somewhere down here, right in here. So this is the footprints that I imported. And you can see in my library's footprints, the footprint that I've just selected is this one right here. Double click on that and assign it, and I am done with the capacitors. Next, let's do the resistors. Resistors things are a little bit easier because I'm going to be using the same footprint for all of them. So do a multi-select across all of the resistors, and then go to resistors SMD, remove that from the filter, and I'm looking for 0805 again, metric, this one. Double click, and I've done the multi-assign. Okay, let's see what else remains to be assigned. I've got the 2 connectors here, the 4 and the 5 pin connector. For the 4-pin connector, I will go into KiCad's connector pin header library. Just going to go for the standard 2.54 millimeter pitch so that it works with standard connectors. And this is going to be just going to search in here just to use the filter 1x04, so that narrows down the options that I have. And I can choose any of those, but I'm going to go for the regular 1x04 2.54 millimeter vertical. Double click. Done, and I'll do the same for the 05, so the one with the 5 pins, and I'll go for vertical as well. Right, done with the connectors. Next up, we've got the test points here. The test points are just pads essentially, so I'm going to go to test point library right here, remove the text from the filter. And let's see, lots of options here. I am going to go for a reasonable option, which is say a 1 millimeter pad. Just going to search for 1.0 millimeter. And all of those have got a 1.0 millimeter in the name. Just going to go for this one. All of those are going to have the same pads. So double click on that single pad and I'm done. And I think that is it with the associations. It looks like all of the symbols have associated footprints. I'm just going to do a visual inspection just to make sure that I have all of the footprints that I want. If I make a mistake, of course, I can always come back. If I see in the actual layout editor that I don't like a particular associated footprint, I can always change it. The process is very quick and easy in modern versions of KiCad. It's not a hassle at all like it used to be in earlier versions. It all looks good, so I'm going to click down here on Save Schematic and Continue. And click OK, and we're done. You can see down here that I've got the search tool enabled, which you can show or hide from the View Panels menu right there. And you can see the associations here as well. And you can click around the schematic edge that will pan to the appropriate location to show you the symbol that you've just selected. And let's continue with the validation and error checking. And to do that, we'll use the ERC, which you can invoke by clicking this button right up here on the toolbar, Electrical Rules Check. You can see down here that we've got errors, warnings, and exclusions. There's a few ignored tests that you can see right here, and these are the defaults. I haven't changed anything. Let's see what comes up. I'm going to run the ERC. You can see I've got 4 errors and a few warnings here, and there's a few ignored tests as well. I'm going to ignore the warnings for now and have a look at the errors. Just unchecked warnings just to clean up my list of violations and errors. You can see the effect. So I want to deal with those first, and then I'll see if there's anything that I actually need to do with the warnings. I'm going to click on the first one and see what comes up. Right. So you can see as I'm clicking on items in the list, the schematic editor pans across to the location of the issue. So the first thing has to do with J1. It says pin A4 is a power pin that is not driven by any output power pins. Okay. Click on the component, double click on it actually, and go to pin functions. You can see that pin A4, this pin right here, is marked as power input. I've connected it to the VBus net, but that doesn't really tell KiCad anything about what kind of net that is. And because KiCad expects, due to the electrical type of this particular pin, that this is going to be a power pin, and needs somehow to tell KiCad that I've taken care of that situation, and VBus is actually a net that conveys power. I did that in one of the other nets. I'm just going to show you here. Right here, VSS, I had the same issue, and I actually preempted this error message from KiCad by including the power flag, but I forgot to do it in this instance here. So what I'm going to do is to simply duplicate the power flag symbol, Command D or Control D, and I am going to connect it, say around here, place it there, and then connect it to the VBus net and rerun the ERC, and that should, take care of that. So 3 errors remaining. Next one, that's a big one actually. I totally forgot to wire pin 3 in U1. That goes to ground. So I'm going to reposition this label. So I'm just going to place it here, right on the junction. All right, and then for cell, this needs to be grounded. So I'm just going to copy the ground symbol, place it here, and wire pin 3 to ground. Run the ERC. 1 error remaining, and you can probably figure out how I'm going to fix this as well. It's the same situation as the first error that I fixed earlier. So I'm just going to again duplicate power flag symbol and flip it, and I'm just going to place it here. Run ERC. Okay, good. No more violations. Let's have a quick look at the warnings. So there's a bunch of issues with libraries. What KiCad is complaining is that this J2 component, for example, is using a footprint library with this name that is not included in the current configuration. The error message, I'm just going to put the window up there so we can see it, is for footprint B2B, PH, etc. This one right here, the JST connector. So that's in here. So this library that KiCad is complaining about is inside this file, but it's still complaining. So I know that it's working. So I'm just going to ignore it for now and see what happens once I get to the layout editor. Okay, the next one says that the copy of the symbol that I'm using here doesn't match the original library. I don't remember if I've done any changes to it, but you can see this is the reference for the symbol. Have a look inside that symbol using the editor, And what I suspect may have happened is that I opened at some point a symbol editor and I did something like maybe moved one of those labels around and then saved it. And that caused a discrepancy between the symbol that is now present in the project versus the one in the library. And that's why it's complaining that there's no match anymore, which is fine for me. I don't really care too much about that particular issue, so I'm going to ignore it. Then there's another current configuration doesn't include the footprint library, just like the first one. Next, got this issue here of pins of type bidirectional and power output are connected. So it says that pin 8 and pin 1 are connected. So if you look at this ground symbol, it's got one pin, which is of type power, and then .1 and .2. I can double click, you can see that this is pin 9 and 8. Pin 9 and 8 are of type bidirectional, and there's a mismatch that KiCad warned me about. But looking at it after inspecting those pins and how I've connected them, I'm happy that there's no issue here. So again, I am going to ignore this warning. Same thing happens here. And I'm not going to go through all of them because you can see that the same type of warnings are repeated across the entire list. So at this point, I can either just ignore, click on close and continue with the layout editor, or I can also do things such as right click on one of those warnings and mark it as excluded. You can exclude with comments. Each time I exclude this violation and choose this command, it affects only the single violation that I've highlighted. But if I want to exclude all of the violations of the same type, then I can right click and then choose ignore all, and that will take care of all of them. Again, I'm not going to do that. If you want to reinstate the warnings that you've excluded, just go into the exclusions or show them, and then you can just remove the exclusion from this violation like this, and that will bring it back. Okay, let's close that window and I'm going to save my project, and we are now ready to continue with the layout in the layout editor. Let's continue with the layout editor. There's a couple of ways to get there. We can go via the project window, or we can just click on the same button in the toolbar in the schematic editor. All right, here's the totally blank layout editor. Before I draw the footprints from the schematic editor to layout, I want to do a little bit of setup. First thing to do is to go into the board editor layers and have a look at this. So you can see right now by default, the project is set up to have 2 layers, but because of the complexity and the size and the number of components on this board, it's not going to be impossible, but it's going to be very difficult and tedious to make all that fit in a 2-layer PCB. So what we'll do is make that a 4-layer PCB via the physical stack up. You can see copper layers are now 4, and then just go back to the board editor layers and have a look at the settings here. In the board layout layers here, I can tell KiCad the roles of each one of those layers. You can see that for most of them, the roles are fixed, but for some of them, the copper layers in particular, I can choose a particular role. Now, my plan, as you know, is to have a 4-layer PCB where in the first layer, I'll be placing the actual components. So components will be only on the top copper layer. And on the top copper layer, I'm also going to have the tracing for the signals. I'm going to use the bottom copper layer also for routing signals. For the first inner layer, I plan to use that as a power plane, but to specifically contain a large copper zone for ground. So having a dedicated ground plane helps to reduce noise and provides a low impedance return path for signals. It also acts as a shield between the top and bottom signal layers, and that helps to minimize electromagnetic interference and crosstalk. For the second inner copper layer, this one right here. I'm also going to mark it here as power plane, and that is going to have a variety of voltage levels above zero. So I'm going to have, for example, a 5-volt copper zone. There's going to be a couple of 5-volt copper zones, and there's also going to be a large 3.3-volt copper zone that will provide power to the various components that operate at 3.3 volts. And just like the first inner copper layer, the second one also acts as a shield between the top and bottom single layers. So that's good the way it is then. Physical stack up, you already seen what I've done here. The only change that I made was to change the copper layers to 4. I'll be using FR4 dielectric material for the various layers. So the rest are fine as they are. For board finish, I'm not going to make any changes. Same thing with solder mask and paste, all good. Let's continue with other details now. This is very important, the design rules and their constraints. It's important because this actually relates to the reality at the manufacturing floor. Since I'll be using Next PCB to manufacture this board, Next PCB publishes its capabilities in this page right here. You need to make sure that any numbers that appear in the board setup constraints is equal or larger to the relevant rows in your manufacturer's capabilities. So I'll give you an example. Let's have a look at the minimum track width. You can see that here by default it's 0, which means that you can, according to KiCad, you can have a track that has a width of 0 millimeters. Obviously, that doesn't make sense. So we will need to put a reasonable number in this box. But what is a reasonable number? So we go to Next PCB's PCB capabilities, have a look at where this information might be. So there's minimum trace width and spacing. That looks what we need. There's the number that I was looking for. The typical copper weight is this much here for the inner layers and this much for the outer layers. My plan for this PCB and the final manufacturing is to have a good balance between the performance, and that includes things such as the size, for example, weight, etc., and the cost. As much as possible, I'll be choosing standard settings for the PCB. So you can see here in the PCB quote page, I'll scroll down to around, say here, you can see outer copper weights. The default is 1 oz, but you've got other weights as well for, let's say, beefier boards. But the standard is 1 oz. The rest will be more expensive. So if I go for 1.5 oz, you'll see that the price goes up and the total would be $70. I go back to 1 oz, which is the standard weight for the copper. Look at the difference in price here. Okay, significant difference. So I'll be going for 1 oz. Now for 1 oz, the minimum trace width is 0.08 millimeters. So that's as low as you can go. And of course, if you put that number in here, there's a trace width. The lower you go, the more expensive your board gets. So the smaller the width, the higher the cost. In my case here, I'm going to configure the PCB editor to use a minimum trace width slightly higher than the absolute minimum that the manufacturer is capable of. So I'm going to put in 0.2 millimeters. Now, I've done similar type of research to fill the rest of the numbers, and to save a bit of time, I'm just going to go ahead and finish up with this work. Okay, so this is fine as it is. Next, continue with the predefined sizes. Going to add a few tracks, vias, and differential pair sizes that I'll be working with frequently. So I'll just click on the plus button here to add the sizes. So I only need to type in the number and the millimeters is inferred. So I'll be using 0.2, 0.254. I'll be standardizing most likely around 0.2 and 0.54 millimeters. So the rest are just extras that I'm probably not going to use. For the vias, and finally for the differential pairs, I'm going to have a couple. Okay, so that's it with the board setup. Teardrops, I'm going to leave it as it is. For the length tuning patterns, I'm going to make a small change here because of the sizes of the tracks that we'll be using. I'm just going to make that amplitude a little bit smaller, or half to be more specific. And for the spacing also half. Same thing for the differential pairs. Can make it 0.15 and 1. The last and most important item to look at in the board setup is the net classes. As you can see right now, it's empty. And if I try to add net classes, it's not going to work because I haven't imported anything from the schematic editor into the layout editor. So the KiCad layout editor right now has no clue as to what the various nets are. Got a couple of ways to deal with this issue. The first way is to just cancel out of the setup window and then go into the layout editor and import the footprints and everything else that's associated, including tracks and nets from the schematic editor. And then I'll be able to go back in here and continue with my net classes and net class assignments setup. But the other way, that's actually my preference, is to go back to the schematic editor, go into the setup and set up the net classes here. And then when I do the import of the schematic data into the layout editor, all that information with the net classes is going to come across as well. And then on the layout editor, the only thing that I'll have to do is to set up the various sizes, as you can see here, for each one of the net classes. And the advantage of doing that is then when I start to design any tracks that belong to each of these net classes, the various geometries for that track will be inherited from whatever I've set up in the net class right here. So that's the right way to do it in my opinion. So I'm going to go and do that now. The first thing to do is to set up the net classes up on the top side and then assign nets to the net classes. I'm going to have a lot of net classes set up here. I'm going to fast forward this bit so you don't have to bear through all of my typing. So I've completed the setup of the net classes. So you can see I've got net classes such as 3.3 volt and 5 volt USB and ground that have to do with power. And there's others that have to do with signals such as SPI, sensor data, GPIO, etc. Because I like what my schematic looks like, just got these new net classes to inherit whatever settings such as wire thickness, bus thickness, the color and the line style of the default net class. So I'm going to move down to the bottom part of this window and do the assignments of nets to net classes. The assignment operation uses regular expression-like expressions. So say that I want to set up the net class assignments so that this net, the plus 3.3 volt net, belongs to the 3.3 volt net class. The way I do it would be to be literal and just say plus 3.3 volt. And you see that there's a match here. That belongs to the 3.3 volt net class. Another one would be the 5 volts. I've got a couple of 5 volts actually. I've got the plus 5 volt net here, and there's also the 5 volt bus, this one right here. This plus 5 volt net will be a member of the 5 volt USB. All right, so I've got all the net class assignments. That means nets to net classes. And now that I have the net classes, I'll be able to go into the layout editor and set up the net classes there in terms of the geometry of the tracks after I import the data from the schematic to the layout editor. Let's go ahead and import the schematic into the layout editor. So in the layout editor, I'm just going to click on this button up here in the top toolbar, update PCB from schematic. And let's see, it says it's found most of the components, but it hasn't been able to find a few footprints here. I wonder if this is a issue related with what the ERC showed in the schematic editor. Okay, I may need to reassociate these components, but I'm just going to ignore it for now and drop all the components here because I want to just finish up with the setup. So I'm here in the board setup, net classes. You can see that all the classes that I set up in the schematic editor are now available in the board setup in the layout editor. Here's the assignments. and the classes up on top. And what I want to do now is to populate this table with actual numbers. So each one of these classes will have its own setup for clearance, track width, VS size, and etc. Once I do that, I'm going to go back to the schematic editor and sort out the issue with the missing footprints. Here in the board setup, I'm just going to populate these numbers, start with the 3.3 volts and work my way up. Here I've completed the setup of the net classes, and the main thing to notice here is that I've spent some time figuring out what the appropriate, especially track widths and the sizes and holes should be. The clearance is also important in order to avoid things such as crosstalk. Now, you might be wondering why I came up with these numbers. There's two things in play here. One is I know that any track that conveys power requires a larger track width than tracks that convey signals, because there's a lot more current passing through a power track versus a signal track. So you can see here that the 3.3 volt track width is 0.5 millimeters versus, for example, an SPI track, which is 0.3, or USB data at 0.25 millimeters. And actually, when I am drawing the tracks in the editor, you'll see that in particular for the 5 volt USB track, I'm actually going to make it much bigger manually than what I've got in the net class here, depending on how much space I have around the track. Going to try and design it so that the 5 volt USB track is as large as possible. Another thing to notice here is that I've set those numbers, especially for the width, from experience. Now, if you want to be more precise in how you set up your tracks, you can use the calculator. So go to the calculator tools, and one of the tools here you can see is the track width, and you can sum up the maximum current draw from all of the components on your board. Let's say that it is, say, 1.5 amps, and then let's say the conductor length would be, say, about, let's make it 15 millimeters, and let's say that for a, let's say, 5 mil thickness track, the track width should be 0.14 millimeters. This number relates to external layer tracks. Remember that most of my power tracks are going to be internal. So if I apply the same numbers to an internal track, then you see that the track width for the numbers that I've selected goes to 9 millimeters. So my estimate is that this board would draw a maximum of around 450 milliamps. So that number here would be let's make it 0.500 amps. And that would be the draw when the ESP32 is at its maximum performance. The BME 280 doesn't really draw much. The Max 4466 would draw about 0.16 milliamps, and so on. And let's say that the LEDs are also working all together at the same time. So that would get the board current draw to about half an amp. So for that half an amp, the track width would be 0 millimeters for an internal layer. Okay, so I keep that in mind when I do my drawing. And also, one important reason for using an entire layer, in my case, the second layer of the PCB, for power purposes, is to be able to provide enough power to any part of the board that's needed without the use of tracks. We'll be using entire copper zones to provide power. But anyway, if you are curious and you want to know how to precisely calculate the width of a particular track that is used for a particular purpose, then you can come and use a calculator here. Okay, so we've got the net classes all set up. Now, the next thing that I need to do is to try and figure out what's happening with those missing footprints. Remember, there are a bunch of footprints here that KiCad was unable to find. So what I'll do is go back to the schematic editor and relink those missing footprints. In my previous attempt to import the schematic data into the layout, it partially succeeded. Got a bunch of footprints here, but several footprints, the important ones actually, are not here. If you remember when I did the import, and I'm just going to go ahead and do it again, you can see that I've got errors down here. There's a few imports that KiCad cannot find the footprint for. And I spent a bit of time trying to figure out what that means and why. And I think I have figured it out. I have exported the report from the import tool in text so that I can have it handy. So let's go back to the schematic. I'm just going to put the report here. And let's have a look at the associations tool. I didn't realize it at the time, but I do now. And maybe that's just a new feature in KiCad 9 that I haven't seen before. Maybe it didn't click as I was doing the recording. But see how these items are highlighted with the different color background. These are pretty much the errors. So for example, here's one, cannot add MK1 because this particular footprint is not found. You can see that MK1 is highlighted and so is Q1 right here. There's Q1 and so on. So I incorrectly assumed that these footprints were already associated with symbols correctly, and that is true. Because when I downloaded the symbols and footprints from Snappeter, the associations were already set. But the way that the associations were set and the paths were set in the originals was that symbols and footprints would be in the same directory. But what I've done in my project directory is that I've got them separated. Here are the footprints, all in the same footprints directory. And here are the symbols, all in their own symbols directory. And of course, these pre-existing associations broke down. Let me become a little bit more specific. Let's go into MK1. I'm just going to search for that. So view, panels, search for symbol MK1, click on it, and it's a microphone. KiCad will take us straight there. I'll double click on this symbol to bring up its properties. Actually, I won't do that. I'm just going to use a side panel here. All right, so you can see in the side panel that there is a library link going to this place here, which I can't edit, but I also want to have a look at the footprints, which is not showing in the side panel. So here is a footprint. The problem is that this footprint is not correct. Okay, it's changed. So I will need to relink the symbols with the footprints. And there's a couple of ways to do that. The first way to do it is to do it manually for each of these components. So since I have my MK1 opened, I'm just going to click on the library button here, and that will take me to the footprint chooser. And in here, I'm going to go into ESP32 project footprints, which I configured at the beginning of the project. And I'm looking for CUI_CMC, this footprint right here. Click OK, and now I have the correct association. Click OK, save, and let's go back to the layout editor and import the entire schematic and see what happens with the specific component MK1. All right, so MK1 has now been edited. See, updated right there. I've got to do the rest. I'm just going to leave it here. All right, let's continue and do the rest now. But instead of doing them one at a time, I'm just going to go into the symbol chooser. And from the left side here, I'm just going to select the project's footprints. So right here is ESP32 project footprints. And let's go and do this substitution one by one. So first SS5240. That, double click, edit. Next is the B2BPH SM4TB. Double click to commit it. Next is GSD0900. This one right here. Double click to set it. Next, TEMT, trans TEMT. That, continue. That's the two buttons. Switch USLPT. Two of those for both buttons. Next is the BME280, and the package is PSON65. This one. Next is the ESP32 module. This one. Next is the Silicon Labs QFN20. I'm going to come back to the QFN20 in a moment. I'm because I'm going to use one of the KiCad inbuilt libraries for that. Next up is this one here is SOIC 127. That. Next, SOT65. And finally, the regulator. It's this one, MPX 3.3. All right. The last item in the list is the serial to USB interface chip. So that's package DFN. For this, I'm actually going to go into the KiCad libraries and relink it there. So that's package DFN. Let's see, DFN QN. Let's enable these filters as well. The one that I'm looking for is the QFN21EP3x3, and making sure that the dimensions are correct. 0.5 by 1.8 by 1.8 millimeters. That's the one. So double click to link it. And now all of them are properly linked. So apply, save, and continue, and click on K. Save the project and go back to the layout editor. And let's repeat the process once again. And that's it. I've got everything imported. So close, and there's my additional components. I'm just going to put them here for the time being. Now that I have all of the components imported into the layout editor, I'm just going to do the placement. And after that, I'll continue with the routing. All of the components are now in the layout editor. So the first thing to do is to work out a way to combine these components together in a way that resembles the final layout of those components on the board. Now, what I'm going to do here is to follow some guidelines that Espressif proposes for the ESP32 module that I'll be using, which is this component here with the integrated antenna. And then I'll be following some more general guidelines as to how to place other components in association with the ESP32, which is going to be the central component. Everything is going to depend on the ESP32 and its position. Aside from those two items, the third guiding principle that I'll be using here is the placement of the various components that the user will be interacting with, such as this component here, which is the SD card module. Obviously, you want it to be at a location on the board that makes it straightforward for the user to insert and remove SD cards. So you don't want to put it right in the middle of the board. And there's a couple of buttons right here. You want them somewhere on the board that makes it relatively simple and easy to press them with your thumb or your index finger. There is the USB module. You want to place that component somewhere that makes it easy for you to insert the USB cable and attach it to the board. And there's a few other components that I would call them as user interface components, including things such the LEDs. You want the LEDs to go somewhere that it makes sense. So you put the power LEDs, for example, near the USB connector so that it's easy to see that the power has been applied when you insert a USB cable. So these are the general principles that I'll be following to guide me through the component placement process. In the next few minutes, I'm going to drag the components and place them on the board in the generally final positions. I may do some fine-tuning a little later, but as far as the location of each component, pretty much where I drop it is where the component is going to stay. One more thing I should mention before I start dragging the components and start the placement process is that I've already had several runs of this. Each time that I did a draft placement, I just improved on the previous one. So what you're going to see is the final configuration of the PCB, which I find quite good and meets all of the three criteria that I mentioned earlier. I'm just saying that so that you know that it's okay to iterate through versions of placement before you start doing the routing of the tracks. So take your time here because it's very important to get this right, especially if you start with the routing and then you realize that placement is not good. You are going to have to undo a lot of work. Whereas if you take your time to go through a series of versions for the placement of the components until you reach a final version that you are happy with, it's going to make the routing much easier and it's going to decrease the risk of having to undo and redo a lot of work. Now, I want to show you a couple of sources of information that guided me with the placement process. One of the data sheets that I've got here is this one here from Espressif. It talks about the physical dimensions of the module. The module that I'm using is this one here. There's another version that doesn't have the PCB antenna. Instead, it's got a connector here that has fewer requirements when it comes to the placement. But since I'm using this one here, the one with the built-in PCB antenna, I need to pay attention to what Espressif recommends. Down here, there's another interesting section, section 11, that talks about the PCB layout recommendations, and there is a link here, module placement for PCB design. There is a reference to this online resource that is this page right here, and here you'll see PCB layout design. Click on that and you'll see recommendations from Espressif. I incorrectly applied a few of those variations. So for example, my very first version of the PCB was something like this, like a rectangular PCB with the ESP32 right in the middle top edge. And my thinking about that was that this way there will be a lot of space around the two sides of the module to route tracks in and out. However, as you can see, the tick mark is on position 3. So the antenna is away from other components, and that puts a bit of restriction on the paths on the right side of the module. Another approved position is position number 4, so the other corner. There's another couple of options here. If the feed is pointed on the left side, then positions 1 and 5 are approved. I kind of didn't like any of those options because the PCB antenna part of the module was sticking out too far, and I was worried that it's going to break or interfere perhaps with the project box that I'm planning to design as well. Luckily, there's another recommendation that Espressif offers, and that is this one here. So there is a cutout of the board, and then you can put the ESP32 kind of in the middle of the board, and the interference is avoided because of the space that is allowed on either side of the antenna, and you've got the dimensions there as well. So that was a bit better. What I decided to do eventually was to go for a combination of the two, both having the module on one of the edges. I chose the top right edge, as well as having the cutout, especially the space here between the board and the left edge of the antenna that you can see right here. And that would give me the best of both worlds, having the module on the right side and enough space from the PCB itself to diminish any potential interference. So that's what I went for. Now what you see here is the final version of my PCB layout, the one that I'm about to start designing here, and it's also the one that is being manufactured right now. And you can see the other elements that I mentioned earlier. You've got the microcontroller on the top right side, and you've got other components with which this microcontroller unit needs to interact at a relatively high speed. So I've got the flash memory and the SD card very near the MCU, just to minimize the length of the tracks for the high-speed signals. There's space around all of these devices for the various capacitors and resistors that are needed for signal conditioning. Then I've got the user interface components along the edges. So you can see SD card right there, easy to access, the USB port, the buttons, the charging port, and the GPIOs all in the periphery. It makes it easy to interact with those components. And there's the LEDs here, quite easy to see. I've got the power LED, you can see right here in the regulator area. And then the sensors are all together. You can see the sensors here. I've got 3 sensors on this board. There's a microphone, the environment sensor, and the light sensor. Having said all that, let's continue with the placement. Most of the time I'll be working with both editors side by side, so the Schematic and the PCB editor, so that as I'm clicking on components, I'll be able to see what's happening with the relevant component that I clicked on the Schematic editor. But now, since I'm just doing the placement and I kind of know what these components are, I'm going to use as much available space as I can in the layout editor. And before I start, I just want to check the grid. For the PCB editor, these are the grids that I'm using. You can see for the footprints, I'm using 0.025 or 0.98 mils precision. I'll be using the grid overrides for this. So this gives me a lot of control. This is a very small grid, so I think it's going to be okay for the size and amount of components that I'm going to work with. So the grid is enabled. Let's begin. I'm going to start with the ESP32 component. I'm just going to put it there. Continue with the SD card. Place that there. You can see that another thing that I can do here, actually I'm going to have the two windows side by side because I'm going to show you a really nice trick that you can do when you're doing the placement. So you can see that when I click on the component on the one side, the same component on the other side is highlighted, and vice versa. If I click on this component here on the schematic editor, you can see that it is highlighted in the layout editor. So I'm going to take advantage of this feature. It's very neat. So what I'll do here is I'm going to select all of the components in the ESP32 group so that they are highlighted in the layout editor, and that way I can pick them apart and put them together. This is particularly important to minimize tracks, of course, but also in this case, it's because for the purposes of signal conditioning, and I need to know which capacitors actually belong to the circuitry that supports the ESP32. So I'll put all those together. I'm going to not worry about the final placement of those smaller components now, but the fact that they are next to the ESP32 is all I need for now. And I'm going to do the same thing for the SD card. Highlight the SD card components in the schematic editor. That picks them apart in the layout editor. So now I can put them all together. Just put them side by side. And I know that it will be easy to figure out which component goes where when I start focusing on these components and the smaller bits and pieces in their vicinity. All right, so that's done. Let's go for the flash memory. And because the flash memory circuitry, as I mentioned earlier, is going to be going for a placement near the ESP32. So these parts make up the flash memory circuitry. Just put them together. So I'll place it here. Next, I'm going to go for the USB module. So now that I have the approximate location of the components, I'm going to draw a box that will start resembling what the outline of the final board is going to look like. Let's go to edge cuts. And because I'm going to have a cutout here, I'm not going to use the box. I've selected edge cuts here. Normally I would just take a box and enclose the components in that box like this, but the box doesn't allow me to have that cut off here. So instead I'm just going to use a line tool. So I'm going to start down the bottom, just making sure that there's enough space on the side of the ESP32 to be able to draw tracks a little later on. You can see my grid size is 0.05. Might actually make a little larger, 0.1 millimeters, and disable the overrides so that I can actually draw at that size. Let's pick up the line tool and start drawing. I'm actually going to go even less. I'm going to go for 0.25 millimeters. Because it's very difficult to draw straight lines on very small grid. I'm using my side-to-side cursors here to help me with the drawing. Actually, before I start drawing, I just want to remind you what I'm trying to do. So I'm going to make sure that there is no PCB below the antenna and that there is a minimum of 15 millimeters on the left side of the antenna. I'll start drawing here, straight line up to this point. Then I'm going to click right here And to make sure that I've got 15 millimeters clearance, I'm going to hit the spacebar on my keyboard to zero the numbers down the bottom. You can see DX and DY. And from here, I'm going to go for another 15 millimeters. You can see that the cursor also tells me how far from the previous click I've gone. So that's now 15 millimeters. I'll give it a little more. Let's make it 16. That's it. And then I'm going to go up. And then continue towards the left. I'm going to go up to here, because I've got a lot of empty space in this board, so I'll be able to make the board a little smaller. I'm not going to commit to anything though, but I'm just going to stop the drawing, say at 90 millimeters, and continue drawing down. I want to make sure that I don't go too far down, so I'll zoom out a bit. Make sure that I go up to the point that I started the drawing at the bottom right corner of the SD card. So around here. That's it. And zoom in to close the line. You can see that KiCad tells me that I've got a closed line because it puts a circle around the point where the two lines meet. Now I've got a board. I'm not going to spend any time here to refine it. I like boards with circular edges. They look modern and pretty, attention to detail. But I'm going to worry about rounding the corners later once I've committed with the placement of the components, and I know that that's where the components are going to be sitting permanently. I'm just going to make sure that everything fits by moving a few things around. And just drag that to the left like that. And I have to do the same with this line. And I'm going to bring this set of components inside as well. Do the same here. Make sure that everything is inside. And then I'm going to start with the refinement. Okay, so that is the first pass of the component placement. I have set the main components in the approximate locations where they're going to end up being anyway. And then all of the other smaller components, especially the resistors and the capacitors, are nearby the components that they support, but I'm going to be fine-tuning them later with their actual positions, and I'm going to be doing that next. So my objective is primarily to make sure that any signal conditioning component, and that is resistors and capacitors, are in the appropriate locations for the main component that they support. And only after I do that, I'll be able to finalize the board layout, and then I'll start with the routing. So now that I've placed the components where they are most likely going to end up on the board, and I've got the rough outline of the board, I'm going to concentrate on the smaller components, and specifically the capacitors and the resistors, which play a significant role to what's called signal conditioning. Signal conditioning involves the preparation of the output from the various components, such as the BME 280, the sound sensor, or even the ESP32 microcontroller itself, to ensure that these signals are suitable for usage by other components. So, for example, signals coming out of the ESP32 to the SD card reader need to be conditioned to make sure that the SD card reader is receiving actual correct signals. This preparation might include things such as amplifying weak sensor signals, for example, coming out of the sound sensor, to match the input range of the ESP32's ADC, the analog to digital converter, or filtering out noise to improve signal clarity, and converting signals to compatible voltage levels. In our project, most of the signal conditioning that we do has to do with filtering out noise, but also we'll be doing amplification in the case of the analog sensors. Before I start manipulating any of the components on the board and just start putting them in most likely their final positions on the board, I just want to talk a little bit about the work that I'll be doing and why I'll be doing it. Things that I'm about to briefly talk about are not things that you'll find in our component data sheet. So I'm going to start with the capacitors first. You can see there's plenty of them. It has a few examples here that relate to the ESP32. These capacitors serve several key functions in signal conditioning. We've got decoupling capacitors, which mitigate power supply noise by providing a local source of current for integrated circuits. And here's one example, this particular capacitor here and its counterpart right here. We are going to place those as close as possible to the power pins of the integrated circuit to minimize trace length and inductance. Smaller capacitor values, such as 0.1 microfarads, should be placed closer to the power pin than larger ones. This arrangement effectively handles high frequency noise and switching transients. And we also have bypass capacitors, which offer a low impedance path to ground for AC signals, and those filter noise and prevent interference with sensitive circuitry. And we position those near the component that requires protection on the signal path side, ensuring clean signals. So I'm going to talk more about those in a moment. There's also bulk capacitors that act as charge reservoirs, stabilizing the power supply by smoothing out voltage fluctuations. And we locate those near the board power supply. So you'll see a couple of bulk capacitors down here. We've got the USB-C connector and the battery connector. There's also resistors. We use pull-up or pull-down resistors to establish defined logic levels on signal lines when they're not actively driven, and we place those near the input pin of the associated integrated circuit connected directly to the appropriate voltage rail. And we use such resistors in this circuit in the I2C interface lines. There's also filter resistors, which work in conjunction with capacitors to form low-pass or high-pass filters. And precise placement is crucial for the filter's effectiveness and requires careful consideration within the filter circuit design. And of course, you probably know about this. There's also current limiting resistors to protect components such as LEDs by restricting current flow. And each one of the LEDs here have a current limiting resistor. Now, I just want to be a little bit more specific about how I use those components, especially the resistors and the capacitors in this circuit. Just want to show you a couple of examples. Let's go to the ESP32 module, and right here, if I search for C8, you'll see there's a C8 capacitor right here. This is this smaller device right here. So this is a decoupling capacitor. We're going to position this capacitor very close, or as close as possible, to the 3.3 volt pin. Yes, as close as I can, and then later on we're going to draw a track that connects pin 1 of the capacitor to pin 1 of the ESP32 module. You can see how close it is right there. In addition to the C8 capacitor, there's also the C7. Just going to rotate that and place that as close as possible to C8, and that's there to further reduce high frequency noise. So the combination of these two capacitor values and the close proximity to the ESP32's pin 1, which is where the 3.3 volt goes, ensures effective decoupling across a wide frequency range. And now let's have a look at another example. Here is U4. This is the USB to serial bridge, and it also requires a decoupling capacitor. So here in the schematic, you can see C11 is a decoupling capacitor that is connected directly to the VBus pin, and it's this capacitor here. If I move it just to see where the rat's nests go, you can see, if I'm just going to zoom in, here's VBus, here's the VBus net as well. I'm going to place that as close as I can. These positions are subject to change as well a little later, because one of my other concerns is to minimize the length of routes and to minimize wires crossing each other. So I may need to rotate the main components as well, like in this case the USB bridge or U4, like this. So depending on which final orientation the USB bridge and other chips have on the board, I'm going to have to adjust the location of the smaller components. But let's say this is VBus pin 8 right here. I'm just going to rotate this a little more so that it has this orientation. So there is pin 8 VBus. And let's say that this would be the final position for U4. I would place C11 like this. So then there will be just a small track to connect pin 8 of U4 to pin 1 of C11. So that's another example of how I would do placement here. Another example worth mentioning here are the input and output capacitors for the LiPo charger. So the LiPo charger, let's search for U1. So here's U1. You can see the schematic as well. There's a couple of capacitors here. Or there is one capacitor to be more exact. There is the input capacitor C6, which I've just clicked on, and it appears here as well. And you can see that there is a plus 5 volt USB net, which is supposed to connect to pin 18 right there. You can see the rat nest as well. So to make that easier to route, I'd rotate the main component like this and the capacitor like this, and now you can see there's multiple USB pads on U1, but I would take one of those and connect it as close as I can to the capacitor C6 like that. That would minimize the length of the traces. The next thing I want to show you are a couple of resistors. These are the pull-up resistors for the SD card. The SD card is right here. Clicking on that brings the schematic or focuses the schematic on the SD card, and you can see there is an example of a pull-up resistor. This is R19, and it's this one right here, and it goes in between the CSSD pin, which is pin number 1 on the SD card module, and the 3.3 volt. I would connect that playset like this, very close to pin 1 of the SD card. Now, another thing that is important to consider that has got to do with routing, not with positioning of components, has to do with routing for SPI signals in particular. So the SPI signals that are connecting the ESP32 to the flash memory and the SD card need to be routed using bus topology. In such topology, a single continuous trace connects all devices. So having said all that, I'm going to now start moving things around and positioning especially the passive components to their final locations around the main components. And then once I do that and have all that fixed, I will remove all empty space by tucking components closer to each other. If you are curious about some more specifics about high-speed layout guidelines that cover things such as transmission lines and crosstalk and return current and loop areas, etc., have a look at this guidelines document from Texas Instruments that covers a lot of the topics that I find very interesting. These are things that you don't find in other data sheets, and you don't find in most books actually, or tutorials. So I find that having a quick look at this document at least will give you some basics or some basic understanding, broad guidelines on how to do all of the above that I mentioned, especially for high-speed designs. Much of what is in this document is a bit of an overkill for the board that I'm designing here, but many other bits and pieces, such as, for example, how to draw traces, vias, actually are very relevant. So look for a link to this document in the description below the video. Let's begin with the refinement. I'm going to start from the right of the board and work my way towards the left. First, with the ESP32, I'm going to use this dual window mode so that I can see what I'm working on and the components that relate to the main component that I've clicked on. Here, I've clicked on the ESP32 module, and you can see the components that are around it. I'm going to be starting with the capacitors to position them, and then with the resistors. So I'm going to place C8 right there, right next to the 3.3 volt pin. And actually one thing that I want to do is to make the rat's nest a little bit more pronounced because I think they're very thin and it's just barely visible. So let's go into KiCad settings, the rat's nest's align thickness to, let's make it 1 and see what that looks like. Yeah, a little better. I'm just going to make it a little bigger. Because there's so many, it really helps having rat's nests that are easy to see. And I'm also going to change that to curved lines. I'll make it a bit thicker. Let's go to colors and look for rat's nest. I think this color kind of blends in the dark background, so I'm going to make it green. Striking. All right, there you go. Now this can't be missed. All right, so this is a good spot for C8. C7, I'm just going to move it here. Then I'm going to go for R15. Move that out of the way. So this is R20. Just move that here for a second. R15. I'll orient it like this. You can see that goes near pin 6. And then R20. That can go there right there. Or, yeah, I want a little bit of symmetry as well. So I'm going to make it like this. Another thing that I've done just now is to click on this rat's nest button and enable a mode where only the rat's nests of the component that I've selected appear. And that just reduces clutter significantly. And then one last thing that I do as I go is I'm going to move the labels around so they're not overlapping. Let's change the filter for this. I'm going to select text. And now that I've got text, I can move these values appropriately. What I'll do as well, just to reduce clutter, is I'm going to make all these disappear. So here, you can see that the value appears. The value, text 50, yeah, I'm going to make those disappear as well, but I'm going to do that across all of the components so that the values don't appear at all. I'm going to double click to see which layer this comes on. So the value appears on the FFab layer. So what I'll do, we'll click on FFab and make that disappear. All right, that's better. Now 20. This is in the front silk screen, so I'm just going to change the color of the front silk screen so that it's easier to see. I'm just going to make it kind of yellowish, like this. That's it with the ESP32. Let's continue with the SD card now. So click on the SD card module and see what we have. I'll start with the capacitors as always. So I've got C12 and C13. C12, just going to move R16 out of the way for the time being. And so C13, so I've selected local rat's nests by clicking on this button right here. So again, that allows me to see the rat's nests for the selected components. Here's a rat's nest for C13. Place that very close to pins 4 and 3 of the SD card. That's great. And let's go for 12. Flip that, and I'm going to place like that right next to C13 and move its label up there. The plan here is eventually, even though the rat's nests are directing my attention elsewhere, so you can see that there's pin 2 on C12 and pin 6 on the SD card module. All I've got to do is to connect those two together and this rat's nest line will be satisfied. So I've got these two capacitors sorted. Then let's do the R19 pull-up resistor, which actually I've done it already. So that's done. And then let's go for R16. So R16, I'm going to connect that or place it probably here, place it here like this. You can see here that the misaligned starts right there on the ESP32 module, and then it goes to this resistor, and then it continues to travel elsewhere. Remember, I'm going to be using a bus topology for the SPI. Now that I have sorted out the peripheral components for U3 and J3, what I can do is to remove this empty space by dragging the SD card and its components slightly up higher, and that would release that space down here. I didn't want to move the U3 component down because I've already taken a bit of time to do the drawing here for the cutout of the board. So I'm actually going to select this bundle of components and lock it in place. And I'm going to do the same for the SD card. I'm going to lock this in place because I'm pretty happy with this configuration. All right. Now I can move this line up a little. This line can go up to here. And that's starting to define the final shape of the board. Next, I'll continue with the flash memory. And I'm also going to move the test points out of the way as well. I'm going to do those last because the specific location of the test points is not really important. I'm going to put the test points in appropriate locations once everything else has been positioned. Let's continue with U6, which is the memory. So U6 has got a capacitor here, which is C14. The orientation of U6 is fine as it is, so no problems there. Just going to move that out of the way. Just going to place the U6 component a bit closer to the board, just to minimize the track length. C14, you can see it's decoupling capacitor for U6. I'll place it near pins 3 and 4. So you can see the traces will be minimal here. Even a little closer would be good. So done with C14, then I've got R22, which is MISO. So R22 will be connected to pin 2. So rotate and I'll position it here. So from here, a line will go there, and then at this positioning, it would be minimal distance to travel to pin 16. So the plan here is that from pin 16, I'm going to do the routing so that the signal reaches the SD card module first, since this is closer, and then it will travel to the flash memory. So this position for R2 is good. And that's it with these two components. So I will select them and tuck them a little bit closer to the other two components, say around here. And I'm leaving enough space up here for tracks to travel from the left side of the board to the ESP32. I'm not going to lock this component in place, but instead I am going to group it together. So now, if I want to do something with it, if I need to move it, for example, just by a little to make room for traces, I can move the entire group of components together instead of one component at a time. I can always ungroup it if I need for whatever reason. Let's continue with the environment sensor. I think I've just noticed an error. Found this resistor R30 that both pads are connected to ground, and on closer inspection, yes, that is true. You can see R30 goes from ground and up here towards pin 3, and then there's another wire here taking it down to ground again, which is obviously not correct. This is something that I didn't notice earlier, and the ERC, of course, didn't notice it. It can't make inferences like this. Maybe later with artificial intelligence, plugins to KiCad will be able to point out that this doesn't make sense. So this is obviously a drawing issue that I didn't notice earlier. So let me just fix it really quickly. This is a good example of what can happen during a live design session. What's happened here is that, okay, this is correct. However, this line here is not correct. I'm going to delete it and move this ground right there. Actually, I move it a little bit further just to make it look a little nicer. But now I've got the ground of the microphone going to ground. I've got the second pin of R29 going to ground, and I've got R30 10K also going to ground. But one thing that I don't have is an extra capacitor here. I need a capacitor in between R30 and ground, which I also totally forgot. So let's do that. There's going to be a 1U capacitor. I'm going to add a new one. So capacitor, just a regular capacitor. I'm just going to put it here. Change its name. This is going to be C19, and its value will be 1 microfarads. And let's put it in place. Move that. Save. And now I need to import C19 into the layout editor. So save and then import update the PCB. Okay, no footprint assigned, of course. So let's add a footprint. Let's go to the associations editor. And here's a footprint that is missing. You can see I went to C18, then to 20. I just missed one capacitor. It's going to be the same type capacitor as the rest for the footprint. So capacitor, SMD, just going to search for 0805 metric like the rest. All right. Save, go back to the layout editor and update the PCB. Cool. And here's the capacitor that was missing. Well, this is very unusual, but it does happen. And it did happen during my recording, which is great because I was able to show you how to fix a forgotten component like this. Very easy, as you can see in KiCad 9. Got R30 here and C19. These two work together. And because there's a capacitor involved, I'm going to give it a bit more space and bring it a bit closer to the active component, the amplifier. Move that up a little. All right, so now I've got, let's check the roughness. Yeah, okay, I've got these two together. So that's in series. I've got that going to pin 3. Then from pin 2, hold on a second. I just noticed one more capacitor missing. So there's supposed to be another capacitor right here, and it's another filtering capacitor on the output of the microphone. Let's fix that. I am going to bring up a new capacitor and just put it here for now. Let's edit its properties. So this is going to be C17, and its value is 10 nanofarads. And that's supposed to go right here in between these two junctions. And let's bring it across to the layout editor. And pretty sure that this is the last omission. Let's go to the layout editor and import this new part. Okay, no footprint assigned, of course. I forgot that as well. So this is also going to be a capacitor SMD 0805 metric. All right, save, and let's bring it into the layout editor. Done. All right, so C17. Let's place it here for now. So I'm just going to do a bit of work now to tidy up the locations for this network. This is slightly different to my original design, where I had the connectors for the GPIOs on the left edge, but I think that is okay the way it is now. It does give us a smaller board. In most cases, smaller is better, but in this case, I don't think that we are actually losing anything from the board by moving the connectors on the top side from the left to the top. Just going to consider one more possibility here, because I'm looking at the microphone and the mic out is on pin 4 of this integrated circuit. So I'm thinking that another option that I have here is to flip this entire group like this. So now the output of this group of components to the ESP32 will be out of this pin here. You can see it right there. So that will make routing a bit easier, and it will also allow us to have the microphone, which is a relatively large component towards the outside of the board. And again, you can imagine if this is in a box, then you can have the box with an opening on the side here just to allow for sound waves to be captured by the microphone without other components interfering. There's still room for changes, so I'm just going to save a little bit more space while I'm at it. And I'm going to further refine the outline a little later with rounded corners, but for now this is fine. So save. That's what the board looks like at the moment. Alright, so the next thing to do is to start working on the routes. So I'm going to start drawing routes and copper zones. So I've got the placement all done, so I'm about to start with the routing. But before I do that, I want to take a few minutes to refine the outline, because I think now this is going to stay like this. I don't think I'm going to need to make any changes in the future. But refining the outline simply means, in this case, to replace these sharp corners with nice rounded corners. And KiCad 9 can do that really, really quickly, as you're about to see. Another thing I'm going to do is to add a few mounting points. I'm going to use up all available space that I have, and let's select the edge cuts layer. What I need to do, I'm going to show you a really nice trick. This process of rounding corners used to be very tedious in the past, but now it isn't. So I've selected graphics right here. I've selected edge cuts. Okay, so I've got graphics selected. I'm in edge cuts layer, so I'm going to type Command A or Control A to select all of the edges. And you can see down here I've got 6 selected items. These are the straight lines that form the outline of the board. And I'm just going to right click on one of them, go to Shape Modification and select Chamfer Lines. And from here, let's say 2 millimeters. You can go like this, I guess. That's okay. Or let's try one of the other shapes. Shape modification. Let's try the fillet. I'll go for 2 millimeters again. That's pretty nice. Actually, I think maybe reduce the rounding a little. So undo. Try again. Shape modification. Make it fillet. And make that a 1 millimeter fillet. Yeah, that's much better. That's pretty nice, actually. I'm inspecting for any issues with overlapping edges or lines and components, and looks fine. One that didn't work is this. Type M, override lock, and just move it a little bit to the left. This is why this corner was not modified. It was because it was selected to be locked. I'm going to type the L key to unlock it. Now you can see it's no longer locked. So I'm going to select this and this edge and right click and shape modification, fillet, make it 1 millimeter. All right, there you go. So this would have been done automatically by KiCad along with all the rest if this particular line wasn't set to lock. But that's fine. So that part is done. For the mounting holes, I'm going to select mounting holes from my footprints library. I'll make it 2.5 millimeters in size, which is a nice size, not too big, not too small. Override lock, move that in a little and create a duplicate and put one here as well. And then I'll place one more mounting hole. That's enough. Let's continue with routing. Now, when I say routing, I don't just simply mean creating the copper tracks that convey signals and power, but also things such as copper zones, and then also making a distinction between critical signals and non-critical signals. Plan is to start by creating the copper zones for the ground, Then the copper zones for power, the various voltages that we'll be using, including 3.3 volts, the 5 volts, and there's a few other nets, for example, the V-bus nets that I create copper zones for. After that, I'll focus on the differential pairs. Then I'll go for clock and high-speed signals. So that means the SPI interface and the I2C interface and anything that is connected to those interfaces. And then I'm going to work on power traces. So anything that conveys power that is not already connected to a copper zone. And finally, the various other signals that are left. After I finish all that work, I will be doing an optimization. One thing that people often do at this point is to use the auto router to take care of the routing in literally just a few minutes. But for a board like this, I find that the auto router produces, of course, results that validate through the error checker, but they're not optimal, and that can lead to problems with signal conditioning, or then you having to spend time to fix what the auto router has done instead of doing the work from the beginning on your own and producing a much higher quality result. So I'm going to skip the auto router and I'm going to go straight into manual routing. The first thing that I'll do is to create some copper zones, and I will start with the simplest one, which is the copper zone for the ground level. I've decided to place that in the second inner copper layer. So I've selected into.cu or into copper from the appearance layers menu. And I'm going to now go ahead and use this tool, draw field zones, and I'm going to draw an outline in a moment. So I've got into, I need to configure it first. I want to connect this zone to the ground level, and I'm going to call it G&D, so zones now can have names. The rest of the items here look fine as they are, and it's going to be a solid fill. I find solid fills perform better than the option here is a hatch pattern. So go for solid fill. Click OK and then continue to draw. And your drawing doesn't need to be that detailed in this case. All you've got to do is to enclose the area of the board where you want the copper zone to be filled. Then because of the board outline, KiCad is going to ensure that the zone is fully contained within the board. So I'm just going to save that, and I'm going to fill the zone. Just right click, zone, fill, and now you can see it designed and pretty much implemented. So this is in the inner second copper layer. Let's continue with the first inner copper layer now. I'm just going to click on this button to make the filling disappear so that the board is still readable. I just noticed actually this. I'm going to lock this group like that. Now, if you're wondering, just before I continue, it's okay for these test points to be out here because, as I said, I don't know exactly where I'm going to put them yet until I start doing the routing. So that's why I've got them out here for the time being. So I'm now working the first inner copper layer. I'm going to start with the biggest 3.3 volt copper zone, which is the one that supplies power everything. It encloses the connectors up here, the sensors, the ESP32 itself, and the 3.3 volt regulator, and also part of these USB circuitry like here. I'm going to draw the 3.3 volt copper zone to enclose these components. There's two more zones down here. There's one around here for the battery, which is going to be the +5 USB copper zone, and one more around here, which is the V-bus copper zone. So those are going to be much smaller. So I'm going to start with the 3.3 volt first. Grab the tool for the zone, start designing. So around here, this is inner one copper layer and 3.3 volt connected to. So I'm going to name this 3.3 volts, and the rest are fine as they are. Right, so now I need to be a little bit more careful about how to draw this. So I'm going to go up to around here. Continue. This includes this area here. It includes the buttons. And it includes the R32, so I'm going to go inwards like that towards the left. And after that, I'm just going to move in a bit broader terms to finish the drawing, because everything else at that point is going to be 3.3 volts. Let's fill all zones. Take a look. And click on that button to be able to see it. Going to uncheck everything else. I'm going to uncheck into copper zone so we can see the 3.3 volt zone that I just created. Right. Looks good. Now I'm going to focus here because I'm going to have a 5 volt for the USB right there, dedicated, and then a smaller one around here for the V bus. Let's do the V bus first. So I want the V bus zone to convey the V bus level from these pins as B4, A9, A4, and those pins up here, number 5 pin, number 1, etc., and number 1 from the fuse. So this is going to look like this. Let's pick up the tool again. Start here. This is going to be V bus. I'm just going to use a filter for this. So V bus. I'm also going to call that V bus. And start drawing. You can see part of the polyfuse is under V bus, and the other part is not. Let's go like that. I'm going to go up this way because I don't want C1 to be enclosed. And close it right there. And as I was doing that, I just noticed that this actually C1 needs to be flipped around because I need to connect pin 1 of C1 to A9. So I'm going to ungroup and then unlock this specific component and then rotate it like this. Group these two together again. And lock it. All right. So let's fill this zone and have a look. All right, so that's what it looks like. And the final zone that I want to create here is in the battery circuitry. And this is going to be the 5 volt USB bus. So take the copper tool. This is going to enclose everything. I'm just going to create a box out of this. This is 5 volt USB, and I'm going to call it plus 5 volt USB. And do the drawing as a big box. And I want to enclose this part of the polyfuse, because as you can see, that's on the 5 volt net. Okay, let's refill. You can just type B to do the refill. All right, cool, that's done. I'm going to continue on the front copper layer now because there's a few zones that I'd like to create here. There's also some tricks that you can use in order to connect pads that are in the front copper layer with zones or tracks that are in a different layer. So for example, notice this pad here. This bus is very important because this is the bus that provides power from the battery to power all of the components on the circuit. So you need to make sure that there's plenty of copper to provide enough capacity for whatever current is needed to flow through. So I could do this in a couple of ways. One way would be to just have a single wire and then put a via here and then connect it, as you can see, to the 5 volt layer, and KiCad did that automatically because it knows what net I'm using and where this net needs to connect to. So it connected it automatically to the 5 volt USB net in a copper layer. But now you only have like a small, tiny, essentially copper track. And this track, it's only 0.25 millimeters. It's probably barely enough to convey enough current to power the entire circuit. Another way to do this is to use copper zones. So here's what I'll do instead. Now let me show you how we can connect a pad pad on the top copper layer with a copper zone in one of the other inner layers. In this case, I've got the polyfuse and I've got an inner layer that I want to connect to. You can see that the green zone is the one I want to connect to. I'm going to start with the vias. I'm going to use vias to do the actual connection. So I'm going to start with the vias and then create a zone to enclose those vias on the top layer. One thing to do is, because we're talking about power here, I have selected a larger via size, 0.5 diameter and 0.3 millimeters for the hole. Let's pick the vias tool first and let's drop the first via here, one more here, and one more here. So I'm going for 3 vias in this case, and each one is going to do its bit to convey power. I'll move all 3 up a little for symmetry. Like that. I can even go a little bit closer. Next, I'm going to pick the zone tool and start drawing, say, around here. I'll connect that to the 5-volt USB net and give it a name. So it's going to be 5-volt bus top. There may be more of these, but I'll use numericals. Then, instead of thermal reliefs, I'm just going to go for solid and start drawing here. And close the pad completely and close. Type the B key and fill it up, and now you can see that there is a really nice connection between this pad and the 5-volt USB zone in the inner one copper layer. I'm going to continue and do the same thing on the other side for V-bus. Done. Next up, I am going to work with copper zones around here to connect the ground pad of J2 to the ground zone in the second inner copper layer. And then I'm going to create a couple of copper zones for U1. One is going to be for VBAT and the other one is going to be for ground again. So let's start with the ground pad for J2, and I'm going to use the same technique. First, I'm going to select the front copper layer because that's where I'm going to create these new zones, and continue with the pads first. Pad, again, I'm going to go for 0.5 and 0.3 because I want these to be quite beefy. All right. If in your case, the vias that you create are not connected to the appropriate zone, all you have to do is to select them and then through the properties connect it to the appropriate net zone like that. So now that I've got that done, I'm going to create a zone. So let's start, say, around here. This is going to go to ground and I'll call it GND. J2. Solid pad connection, and just enclose part of the pad and the ground vias. All right, B key to redraw. Looks good. Okay. Next, I'm going to create a new zone right here. That zone will enclose pads 15 and 16. It's because I want to then use a large track to connect VBAT, which is pin 2 on S2, with the zone that combines pads 15 and 16 of U1, because there's going to be a lot of current flowing through this single track to power all of the components on the board. So I'm going to make it very big, as big as I can. Let's go and do that. I'm still in the front copper layer. Take the zone and start drawing here. I want this to be connected to VBAT. And I'll call it VBAT top 1. Solid fill. Make it big here. So that's the zone created. And just so to show you what I mean by connecting this pad to this zone, I'm going to go ahead and do that now. I'm going to type the X key and start drawing. And connect it like this. So front copper layer. Okay, I need to type the B key to make sure that the connection does apply. And have a look at the zone. All right. Just notice that I've got pad 14 as well. That needs to be connected. So I'm going to simply extend the zone to include pad 14. I can't select it again. So let's go to the search panel. VBAT. All right, so I want to extend that a little higher to include 14 and 16. All right, let's redraw. Right. For some reason, pad 16 is not included. And I'm thinking this has to do with the clearances. So I'm going to make the clearance a little smaller, 0.2, and see if that helps. Oh yeah, it did. Okay, so that was a problem here. All right, so I'm going to repeat the drawing just to finish it up properly this time. So X key to connect. Done. All right. And one thing that I'm going to double check as well, again, one more time, is to make sure that this zone is assigned to the correct place. Yeah, VPAD. All right, let's continue. So I'm going to create one more zone to enclose or to combine these two pads together, the two ground pads. That's ground. And I'm going to use a via to connect that pad with ground. So it goes to the ground net. Done. Draw. Just notice there's one more zone to connect here, and that's the 5 volt. Again, two pads to combine together. And I'm going to have a track coming out of that. Let's view it. Yeah, that's better. One thing that I forgot to do was to give this zone a name. Or did I? Yeah, I don't think I did. This should be G&D top 1. Right, G&D top 1. Yes. Okay. I'm going to move up. There's a ground copper zone in the regulator set of components that I want to create. So here's a regulator. You can see there's 1, 2, 3, and 4 ground pads that need to be all connected through to the ground zone in the, to copper layer. So let's do that. Front copper layer, let's pick the zone tool. So let's start drawing. I'm going to create a zone that encompasses these pads. It's going to be connected to the G&D net, and I'm going to call that top 2. All right, so start drawing like this. Done. And now to make the connection to the copper zone in the second inner copper layer, I'm just going to use a bunch of vias. I can now select them all and change the net to G&D. All right, so draw. They look a little ugly, so I'm just going to align them better together. That's enough. Let's save. Don't lose any work. Next copper zone to create is this one here. So that's pad 4 of VR1, and I must create a copper zone to provide a low impedance path to the 3.3 volt copper zone in the inner one copper layer. I remind you, this one here. So let's create, actually before creating the zone, I'm just going to drop the vias. Let's put a bunch of vias here like this, and all of them should be connected to the 3.3 volt zone. I'll align them to top, and I will distribute them nicely horizontally with even gaps. And now let's switch to the zone. I'll start from up here, and that's going to be 3.3 volt. I'll call it 3.3 volt top 1 and close them. Done. And I think that's it with the zones. So you can see the zones that I've created down here in the search panel under the zones tab. And I think that's it. I may need to, of course, create 1 or 2 more as needed as I'm doing the actual trace routing. But I think for now it's good enough. So I can then continue with the differential pairs followed by the clock and high speed signal traces. Let's continue with the differential pairs. On this board, there are two differential pairs to route. The first one is down here. You can see I've got USB DP and USB DN. Those pads up here need to be connected to this and this pad right there. And then a little further up, I have USB D plus and USB D minus. Right here, two pads and the other two pads down here. Let's get started with that. I'm going to select the differential pair tool from here. The problem that I'm having here is I'm clicking, revealing the menu. I'm trying to select differential pairs, but it won't let me. So I'm going to try by using the keyboard shortcut, which is 6, and start from the bottom. So again, with the 6 to start the pair. Now it's going to probably work. Maybe not again. So the problem here, maybe it's positioning, but also you can see that there is a clearance. The pads up there are very close to each other, so the clearance may be a problem. The first thing I'll do though is to move U4 a little bit to the left so that it's properly aligned. I'm going to unlock it and just move it a little bit to the left. Then try again with the differential pair. Now this is still not helping very much. I'm going to try again with a smaller track and clearance. So let's try that. 6 shortcut and yes, this time it did work. It's not very nice though, so I'm just going to move U4 a little bit to the left, just a little more, and clear these tracks. Attempt once again. So 6 instead of X, start drawing. Yeah, and now they look better. So that differential pair is done. Let's try the other side now. So I've got DP and DN down here. Start drawing here. I've already got the appropriate tool selected, but you can see I can't get through because of the V-bus pad in the middle. So I'm going to try from the other side, top to bottom. One thing that I'll do is to see if I can move these two components a little higher. So I'm going to unlock and move up a little. And that should not affect the differential pair drawings up the top end of this component. Now that I've got a bit more space between the two pairs of pads that I'm trying to connect, I'm going to start again. Typing 6 on my keyboard, starting to draw. I'm going to go up to about here and then finish. Yeah, and that worked. Problem here is that the V-bus pad will need to be connected to the V-bus net. I prefer to do it around here using a via instead of some other way, passing tracks in between those pads. So what I'll do is I'm going to drag and redraw those lines that I already drew using the differential pair tool. So I'm going to use the D key. The D key allows me to drag in 45-degree mode. So D, and let's move things like this here. And like that, and just fix that bit down here a little more to have symmetry. Yeah, that looks good. One more thing I'm going to fix is these two segments. So that's it with the differential pairs. Next up, I'll work on the tracks for the two high-speed interfaces, especially the SPI, and then I'm going to work on the I2C as well. I'm going to continue drawing the tracks for the I2C interface, and those tracks include the SCL and the SDA lines. The good news about this is that I2C typically operates at speeds of up to 400 kilohertz in standard mode, and we're not going beyond that in this example application in this PCB. It can go up to 1 megahertz though in fast mode, and at these frequencies, minor differences in track lengths won't cause significant skew or timing issues. Also, perfect matching of trace lengths is not critical for I2C. Still, I'm going to try and keep the lengths of those two tracks as close as possible. I need to pass those tracks through the BME sensor, and from there it will also travel to the header for the display. Another thing to remember about I2C is that you want to keep those traces away from high-speed signals and other potential sources of interference. The good thing about the layout of this design is that the SPI components are down here on the board, and there's one, of course, here. I'm going to move it a little bit further down, and that leaves the traces for the I2C quite isolated on the top end of the board. Okay, so let's do that now. As I said, I'm just going to move U6 a little bit to the bottom or towards the bottom of the board. Lock it up again. I'm just going to pick the normal drawing tool. I can just type X on my keyboard and start drawing. This is on the top side of the board. Click there. Then I'm going to connect SDA as well. Like this. Just improve traces as I go. Minimize wasted space. After that, I'm going to connect the two SEL traces together, and I'm going to go in between the pads and connect that to pad 2, so I don't have to switch layer like that. From here, let's continue. Going to continue with SCL across the corner. That goes all the way to pad 15. So at this point I will switch to the bottom copper layer, use a via for that. Continue up to about here, and then go back to the surface via and connect to SEL. Let's do the same thing for SDA. Start drawing at the top copper layer. Gonna fix those ugly traces in a moment. Here, switch to the bottom. Continue up to around here. And that, oh, actually the SDA is all the way back here. So let's retrace. I'm going to move this via. Since I've already drawn it, I'll move it here. And then from here, go to the top layer and with X, continue to SDA. All right, so let's fix the quality of this drawing. Okay, that looks much better. Now, one thing to notice, of course, is that SCL, the clock, is much longer than SDA. I would actually like to improve that and get them as close as possible. To do that, I'm going to start by checking out to see exactly how long these lines are. You can see down the bottom that the routed length for the SCL line is 68.29 millimeters. The number for SDA is 52.03. Going to do two things. If possible, I will reduce the length of SCL, but I don't really think it is possible. Looking at how it's configured, I don't think it's possible to reduce it. Therefore, the other thing that I can do is to increase the length of the SDA line. There's a couple of ways to do that. One simple way would be to just waste a bit of space here. Well, not waste really, but use the available space under the ESP32 to try and improve the length. You can see as I'm doing that, the total length for the SDA line is increasing and is now at 59. It's getting closer. Another thing that I can do is to use a tool that KiCad provides for length tuning. So up at the route menu, you see there's an option here using the 7 shortcut key to tune the length of a single track. So let's try this tool out. Select that. I want to change the length of this particular track. You can see right now it's 41 millimeters. If I start clicking and drawing to the left, so I clicked, held, and then started drawing, you can see that that length goes up. So you still need to go up more, so I can continue elsewhere on the track. So now it's at 54, 57. I just reached 59. So now they are very close to each other. I'm going to hit escape and check to see what the length is. And you can see it's now 77. So the whole thing is actually bigger than it should have been. I can then continue to fine tune. So let's say I will make this smaller. Just click somewhere else to see what it is like now. 67. Yeah, actually I'm pretty close now. One thing that I don't quite like is this area here. I'm just going to make this a little smaller. Like this. Make that a little smaller like that. And let's see now. 66. Yep. I'll do a little more fine tuning. And now I've got 68.9. Yep. That's actually pretty good. 68.9 versus 68.29. That is well within the tolerances. Some last fine tuning, 68.85. Yeah, I'm going to leave it at that. So I'm pretty happy with this result. So that's I2C. I2C is now fully connected. And I'll continue with the SPI interface down here. Let's continue with the SPI interface. The SPI interface has pads on the right side of the ESP32. There's MISO, and there's other involved pads on the left side as well. And those routes have to go through to the SD card module. There's clock, MOSI, CSSD, and this pad here as well for MISO. And there's also the flash memory here. I'm going to move this module a little bit higher, select it first in the filter, then unlock it so that I can move it. And I'm actually going to move that a little higher and the module with its components a little lower and place that mounting hole there. Might change position again later, but for now that's okay. Lock it again in place, and I'm going to start drawing from here. That's the furthest away, and there's also pad 18 that I need to route. I'm also going to place the test points to the final locations. I'm going to do that once I know where the SPI tracks go. I'm going to start with MISO and start the track on the top layer like this. I'm going to route it under the SD card. You can see that that is going first to R16, but I want to route it to the flash interface right there to begin with. Now this is a good place for TP2, which is MISO, so let's grab that. And I'm going to place it right there, right on top of that track. So I don't have to do any more work for TP2. Done. Next, I'm going to connect CSSD, so that's the select signal for the SD card. That needs to go right here. So I'm going to start from the front copper, type X. I'm going to need a via here to the bottom and continue down this path. Around here and resurface and connect it to CSSD, and that is also the pull-up resistor. And while I'm at it, I'm going to take TP4 and connect it right there on the line. One thing I need to fix here is that this line, as you can see, is 90 degree, which is a bad idea. So let's see if we can fix that. Yeah, that's better. 45 degrees is much better. Okay, let's go back to the memory now, the flash memory from here. I'll enable the RAD nests so I can see what else is happening. So you can see there's a connection from MISO to R16. That's R22 to R16. So let's draw that like that. And from R16 straight down to pad 7. Like from the other side of R22. Let's finish up with the interface. See meso signal to U6. Now let's work on MOSI. And then we'll work on the clock. You can see this MOSI pad from U6. That goes right here on R15. And actually I'll do the clock while I'm at it. And that is a good location for the TP3 test point for clock. Just plug that right there. There's clock. Yeah, move it up a little. Just to improve the clearance. Done. R15, the other side goes right there to pad 6. And for R20, the other side goes to pad 5. There's also a connection between pad 2 of the SD card to pad 2 of R15, so I'll do that now. Should be able to route all that on the top layer. Just going to go this way and connect it there. Just noticed that I made an error here with the way that I connected the MOSI pads together, and the error is that I connected those together in a radial topology. It's better for SPI components to be connected to the microcontroller in a bus topology. So what I'll do is remove this track here. So get rid of this track. You can now see that MOSI is going via pad 6 through R15, first to pad 2 of the SD card, and then from here I'll connect it to pad 5 of U6. We've got a couple of options here as to how to cross that line here. I can go to the bottom layer, but that is not optimal because of the high-speed interface. I'd rather keep as much as possible everything on the top layer. But I'm looking at this resistor here. The gap between the pads of R16 is big enough for the track to go through. So what I'm thinking is I can use that as kind of bridge. I'm going to move R16 here and use it as a bridge so that the MOSI track can pass through the two pads without having to go to the bottom layer. That will require a little bit of moving things around. So that means, let's override this lock. Let's move this up there and delete those tracks here. And as a result, I'll be able to easily connect MOSI. This. Done. That was easy. Let's continue. Going to remove this bit here. Go a bit closer. And then from here straight up. Restore the broken connections. Alright, I think that's much better. Let's continue with the clock. Started the clock here, then the next connection for the clock is to go to the clock pad of the SD card. Just going to go in between pads 7 and 6 and finish the connection there. There's also the chip select goes to, I'm going to move TP5 here, and let's see, chip select for the flash memory goes down here. All right, so that's going to be a long trace. So let's go from here to here, and then I will need to switch to the bottom layer. I'll do that here. Continue until around here and switch to the top layer to finish up. The last thing to look at is the length. The most important track here is the clock. So we want the clock to be as short as possible, and therefore let's measure it. The total length for the clock is 26 millimeters. The total of MISO is 63.3 millimeters and MOSI 51. The main thing here is that the difference between MISO and MOSI is not big for the total size and the frequency of operation for the SPI interface. And the good news as well is that the clock is much smaller than the two, which is the more important consideration here. The clock line is the most critical in terms of timing. So this is the shortest, and it's actually a fairly clean path. So I'm pretty happy with that. The other two traces, MOSI and MISO, are bigger compared to the clock, but I'll see if I can make them any smaller. But before I do that, I'm just going to move TP1 to, let's say, maybe what would be a reasonable spot for it. I think here would be a good spot. There is a conflict, so I'm going to move TP1 a little bit to the left so that I can accommodate TP1 without a conflict. So having done that, the next thing I'll try to do is to minimize the length of those lines as much as possible. They're not bad the way they are now, but I think at least, see, MISO can be somewhat smaller. I don't want to make MISO flip to the bottom side though, so I'm going to continue working like this. Make that a little bit smaller like that. So we are now at 62. Yep, so we saved 1 millimeter with the work I've done so far. Another thing that I can do is increase the size of MOSI by a little. So like that, just to make it a bit closer to MISO. It's now 52. Yeah, not a big deal. The interactive router did something crazy here, and it rerouted the nice clean route that I had to this weird shape. So I'm going to hit undo a few times to undo this work. That's better. Yeah, I'm going to leave it at that, and if needed, I'm going to come back later and see if I can make any further improvements. That's it. Okay, I'm going to stop here, and then I'll continue with the power traces. So anything that's got a voltage or ground, I'll be routing it and completing it. Let's continue with the power traces. This includes connecting pads such as the ground pads here, the 5-volt USB pads right here. There's another 5-volt V-bus. There's also a lot of 3.3-volt pads, and all those will be connected using vias to the appropriate copper zone in the inner layers. And I'm going to do that in segments. So I'm going to start from the bottom left corner of the board and then work my way up and then to the right and so on until all of those pads are connected to the appropriate copper zone and nets. So I've got a ground pad here and the 5-volt USB pad. The technique is the same regardless of what pad it is. I'll create a trace to connect this pad to this pad here and move it to the side a little. And then this pad, I'll go to the appropriate copper zone using a via. You can see that that's connected. I'll use the same technique for the other pads as well. So for the ground, I'm simply going to use a via for this. Done. In the center of this IC, there's a big ground pad, and I'll connect it to pad 3 and to pad 10. And from here, pad 3, I'll just break it out to a via like that. I'm going to come back to the 5-volt pad and zone here. I've got 2 more USB pads here, so I'm going to simply break them out using vias like this. Of course, I could connect it to this pad here, but I prefer this method here as well. So I'm going to add 1 more via like that. There's 2 more USB 5-volt pads, so continue with the same technique. Break them out using vias. Done. All right, this looks okay. Remember that I'm not working with signals now, just with anything that relates to power. There is a large track that I'm about to create that will connect the 5-volt pads and zone to this set of pads. So for that, remember, this is important because this is the track that supplies power to the entire board. So I'm going to use a large track like this one here. This is a 1mm track, but I need to pass it through the polyfuse. So I may need to make a bit of room to get it through. So I may need to actually move this component a little bit to the left. So let's choose it. And I'm aware that there are 2 copper zones here as well. So I'm going to unlock this component and make sure that I can select everything on it and move that slightly to one side and up to make sure that there is enough space here for the big track that I'm about to draw to go past. Before I continue, I just want to make sure that I didn't break anything. And I can see that the connections are still fine as they are. Yeah. All right. So from here, I'm going to draw. Let's switch that to 0.8. I'm going to create one more track size. That's going to be 1mm. So that I don't have to make a change later. So go for 1mm and draw this huge track. Oops. Yeah, it hasn't picked up the fact that this belongs to the 5V net because I didn't touch it to one of those pads. Select the entire track and assign that to the 5V net. Should now be able to connect it. Not sure why it didn't pick it up automatically, but it's okay. We can fix this through the properties. All right, that should be it. It's done. Yep. So that part is complete. Let's continue with those ground pads. This will be easy. I'm just going to go back to use net class widths and connect those together like this and see if there's enough space for vias in between. Yeah, I would do that. That's fine. I use a similar technique for these. So X and vias. Done. These ground pads are already connected to the ground copper net. Now let's work on the 3.3V nets. I'm going to use vias for this. So X to draw a short trace and then V to go down to the 3.3V copper net. Same thing. V. Connect these two together. That's ground, so break it down. These two go together. So one of the benefits of using this technique is so that you don't draw long wires that may make it harder later on to draw other wires past them. So they're not blocking the space between different parts of the board because these are so short they don't obstruct. R11. Done. I've got C1 ground and V-bus that needs to go in here. Do need to choose a smaller trace for that, and there's a V-bus there as well. Right, so let's see, this is too big, unfortunately. I'm going to have to override the net class width with something smaller. Let's see if that works. And then VIA, yes, that did work. And then V-bus from here to C1. Great. Another V-bus from here to right there. Done. Ground. Connect those ground pads. These are through-hole pads. Connect them together. the proximity between those pairs is convenient, so I can just create the connections using short wires. On the other side, I've got ground. Oh, there you go. Something that I forgot to do earlier is I've got the differential pairs for the USB. These are the alternate USB through holes on the USB connector. So I've got DN and DP, and you can see here DP and DN, but I also need to connect those and to terminate them right here as well. So I'm not sure if I can do this as a differential pair. I should be able to do it, so I'll give it a go. So I'm going to stop working on the power nets for a moment and do this differential pair before I forget. I'm going to start with B7, type 6 on my keyboard and start drawing. No, that's not going to work. All right, I'm going to start with the bottom copper layer and try again. 6 on my keyboard. Yeah, okay, so that's what the problem was. Right, so let's go around here and then maybe, let's see, I'm going to need to break to the top layer. Now, I've got a better idea. This is not going to work. So what I'll do is, because I want to minimize how many vias I use, and as you can see, it's a pretty busy area here. What I'll do is I'm going to use the 2 inner layers to help me with this situation. What I'll do is I'm going to break out these 2 tracks on different layers. So B7, I'll put that on the bottom copper layer, and then B6 in a 1 copper layer. So that way they're not going to be conflicting. It's going to look like this. So I'm going to go for the back copper layer. So select that and then start drawing like this. And here, use a via to break to the top copper layer and finish the connection. For DP, I'm going to do the opposite. I've selected in a 1 copper layer, start drawing here towards the other side. I'm just going to cross here and type V, switch to the top copper layer and finish the connection there. Okay, I just enabled all layers so we can see them, and you can see that here's USB DN and here is USB DP. They're overlapping. I'm just going to just change the geometry a little bit, move this via out of the way because the differential pair wires are more important, and I want to minimize any discrepancies between the 2 signals. So I want to have the 2 traces be as similar as possible in terms of shape and length. Move it down a bit, it's abstracting. Yeah. Okay, I think this is actually pretty good. Just move that down. Remove this segment, it's redundant. Okay, so there you go. That's taken care of. All right, I can continue now with the power pads. Right, so I've got... Okay, I think that's it. I need to correct the widths of some of the 3.3 volt tracks. You can see I've got them at 5 millimeters, but I'm not sure if all of them are. I think some of the 3.3 volt tracks are not at least 0.5 millimeters. You can see this one here, for example, it is smaller, and the same thing goes with the vias. So what I'll do is I'll go to edit and then edit the track and via properties, I want to make sure that all of the items that belong to the 3.3 volt net will have a track width of 0.5 millimeters and a via size with a diameter of 0.5 millimeters and a hole of 0.3 millimeters. So that's going to take care of all of those. Right, it's done. I'm going to double check to make sure that I haven't broken something. There are two even more important tracks that I need to change even that setting. So you can see here that this particular track here supplies power to the entire ESP32. So I'm going to make it even bigger. I'm going to select the entire track. So select that track and I want to bring up its properties because I want to change its width to make it 0.8 millimeters. That's better. So yes, change all of those. Okay, so bigger is better. And also need to change the size of the via here. And I'll do that. I'm just going to click up its properties actually. So I'll be able to select one of the predefined sizes I've created here. And that is, make it 0.804, like that. Okay, that's better. So I could have done it with the side panel, but the side panel doesn't give me access to the predefined sizes that I wanted to use. Okay, I think that's all I need to do with the power related pads, nets, and vias. So I'm going to continue next with the signals. Anything that's now got a green line means it's not connected. I'll go ahead and connect it. I'll try to stick to the front copper layer as much as possible, but every now and then I will need to switch to at least the bottom copper layer. I'm going to switch back to use net class width and hit X and start connecting at least the easiest tracks. Those ones are going to be easier. Probably going to have to go from the top side because there's just too many through holes here. So let's see, around the back. Nope, that's a bit too tight. Still nope. Yes. Okay, success. It wasn't that easy. It's a bit tight, so I had to change the shape of the differential pairs as well. The previous change that I made here, you can see that it actually had some unintended consequences, and I've got like a huge track that is interfering with the pads, so I need to reduce that size. So let's select these 3.3 volt tracks and bring up properties. Let's see if I can actually no, I'll do it from here. I'm going to make this 0.5. I'll go a bit lower actually. I'll go for 0.24, 254. This is the sensor. It doesn't really require that much power, so that is not a problem at all. I'll do the same thing for consistency for this track. Okay, that's better. Let's look for more signals. I'm going to connect all these together using tracks. Okay, I think I've done all the signals. I don't think there's anything outstanding. Actually, there are. It's because I've been hiding those additional nets. So let's enable everything that I disabled earlier so I can finish those routes. There we go. I was wondering, I knew there were more. It's going to be a tight fit. Yeah, I'm going to need some more space up the top side, but I'll see if I can move this via. No, it's too tight. Yeah. So I will need to move these resistors a little higher. There's enough space for the routes on top of U1. So let's fix this up. Then it goes all the way to the ESP32. Right. So let's go from here. Keep it simple. Switch to the bottom layer. Continue up. From here, switch to top layer. And finish. From here I've got enable, do something similar. Switch to bottom. There's this one here that is blocking my way. So what I'll do is going to move this over here so that these can continue in the bottom layer. Until around here. Similar with this is ground. Make room. This can move over here. Then continue up this way until it reaches the surface right there. Okay, continuing. I've got DTR and RTS, so this will have to go under right away. Until it reaches around here. Same thing we did here. Under. Okay. I only noticed it like a moment ago as I finished the signal routing. I was so concentrated on doing the signals that I didn't realize that somehow, somewhere, I managed to delete the copper zone in the inner 2 copper layer that is for the grounds. So that's why you see all these rat's nests indicating that the ground pads and holes and nets are not connected. Not sure exactly how it happened. I'm going to go back to the video review and see how I managed to do that. But see, I also ran a design rules checker, and these errors that you're seeing are mostly, at least, about the missing ground zone. Let me just quickly fix it before I do anything else, except for this thing here. I've got to fix that route. So it was just too close to those spheres. All right, well, let's go back and fix that missing ground plane. It's just weird how it happened. All right, inner copper layer 1 is where the ground zone should be. Select inner layer 1 for copper. Let's bring up the zones tool, and I'm just going to make a big zone for ground and finish it there. All right, that should be good now. So I'm going to type the B key. It should fix that issue. Let's save. Now, if I look at the search panel, so I can have a look at the zones. Okay, I figured out what the problem was. At some point, I managed to misconfigure the ground and the 3.3 volt copper zones, and I had set both copper zones in one copper layer. So to fix the problem, I simply switched the 3.3 volt copper zone to be in the in2 copper layer as I originally intended. Again, I'm not sure how the problem occurred where I made the change. And that left the ground copper zone by itself in the in1 copper layer. I'm just going to fix the name here. So I was experimenting. I changed the name to GND in1. All right. So then after refreshing the zones, everything is now as it should be. Now there's a couple of things still to fix. Notice that here, the 3.3 volt pads here are not this pad here is not exposed to the other two. So I'm just going to create a new zone just to fix that issue. So let's go for a finer grid, and let's start here. All right, so that's going to be 3.3 volt like that, solid, and everything is good. So let's place that over here. All these are 3.3 volt, 2.54. Yeah, that would do. Connect them all together, and that takes care of that issue. Now notice there's a couple of other issues here. Again, it seems like there's no ground. I think that's because in the in1 copper layer, only ground should appear, not VBus. So VBus should be in in2. So let's fix that. Sorry, that should be in in2. And anything else in one? Yeah, 5 volt USB. That should also be in the second inner copper layer. All right. So redraw. Done. That was a tricky bug. I confused in one with in two as I was assigning the copper zones to the different layers, and hence the problem occurred. Thankfully, the rat's nest lines and then the design rules check make it easy to find the problem, and fixing it is just very easy. Next up, a design rules check. Make sure I haven't missed anything else big, and then continue to finalize the board. My board is about 90% ready to send to the manufacturer. That's my estimate. I know there's a few things that I need to fix, and just looking at this board reduce a bit of the clutter. I can see that somehow I forgot to connect a couple of items together. There's a few tracks that I can definitely improve, remove unnecessary turns, and remove some 90-degree turns as well, such as this one here. But I'm sure that there's also other issues that I can't see right now. Just one more thing that I'll do to remove clutter is to uncheck the highlights or the shadows for the locked items. There's also additional work that we'll need to do in the Silkscreen layer on the top side, just to add more text in order to make my board a bit more professional. So for example, descriptions for the various pins here in the headers and other things of that sort, just to help with the final design. But before I do all that, I am going to run the design rules check just to reveal issues that I can't see. So here's the Redesigns rule checker. I just clicked on this button right here, and I'm going to run it just to get an idea of how much work is remaining to be done. I've got a couple of unconnected items as I suspected. Quite a lot of warnings and errors. Don't worry too much about this. I don't think that the situation is that dramatic, and many of those errors I'll be able to just review them and then most likely put them aside. Not going to have to fix much. Let's do the unconnected items first. Obviously, I'm just going to do this one here. This is the easiest. Front copper layer, tapping X on my keyboard just to finish with this connection, and that's done. And the other one is down here. So for this to work better, I will need to make a bit of room here and here so that I can then create a via and pass the line underneath the board right here and then back to the surface. And I'm just going to improve the wiring like this. Okay, run again. Nothing unconnected. So let's go to the errors now. So this error says that this particular via, and most likely the other one here as well, has got an annular width that is 0. So essentially that means that the hole is equal to the diameter of the via. Obviously, this is not a good idea, and it violates the constraint that I've got here of 1 millimeter. So this is easy to fix. I've got 2 vias to fix here. The first way to fix it is to just double click on the via, bring up its properties, and then go for one of the predefined sizes. And I think because this is a regular signal via, I can go for 0.5, 0.3, and that would fix it. But I'm going to show you another way to do this that is a little faster, especially when you have multiple vias to fix in this way. So go to Edit, then go to Track and Via Properties, and then select out of the filter, a filter or a filter combination that captures all of the items on which you want to make the change. So in this case, I've got the net Q3B, so select that out of the drop down, and then I'm going to go for via size 0.5, 0.3. That's it. So both are now changed together. If I run the DRC, you see that that is sorted. There's other issues to fix, but this one is sorted. Other issues to fix here have to do with the ground. Again, similar situation, and you can see there's a couple of those ground items that need to be changed. That has to do with vias. I'm going to follow the same process and go to Edit Track and Via Properties. This one is going to be for the ground. And I'm going to change this to 0.5, 0.3 again, like that. Run DRC. Then I've got this set of errors. You can see there's multiple, and they all have to do with the vias in the ESP32 footprint. Now, the thing about this footprint, I'm just going to save as I go, is that I'm just going to show you. I'll go to the footprint editor, and you'll see here that these vias are part of the original work of whoever created the footprint for the ESP32 set the vias here to this size. I don't really want to change it. And I've also checked with Next PCB, and they don't have a problem manufacturing the board with this particular geometry here for the vias and the pads. So what I'll do, instead of trying to fix this, I am simply going to ignore it like this. So that takes care of that. I'm ignoring this particular violation because I understand its implications, and I know that it does not affect adversely the outcome of the board that I'm building. So that's sorted. Let's continue. I've got a few violations here. The net class GND clearance 2.0.2, 0.1649. Now the issue here, you can see it's J1 and B1 and B2 are too close to each other. B1 and B2 are too close, and unfortunately, again, there's nothing that I can do about this because that is the footprint of the USB connector. So again, I'm going to ignore all of these. Next, I've got some complaints about thermal reliefs. You can see this copper area here connects G1 to the ground copper fill, and it's just a single thermal relief. Same thing happens here, just a single thermal relief. KiCad would rather have two spokes for the connection between the copper zone and the pad. Unfortunately, we can't fit more than one spoke. So I'm going to ignore that as well. Next, more issues that I really can't do anything about. This one here is about the solder mask aperture. You can see that this pad here has got a solder mask that touches the pad adjacent to it. This is what this complaint is about. So again, I'm not going to do anything about this because I can't really do anything about it, and I will ignore it. And that takes care of all of those violations. Next, I've got a bunch of warnings. What's happening here is that I have a 3.3 volt via connected to this track here. However, this via is not connected to anything else that is 3.3 volts, so that's why via is not connected. So what happened is that the zone above the via, let's select the zones as well. I need tracks, and yeah, that's good. So this zone here is the 3.3 volt zone, this one right here. However, when I created this via, I kind of missed the target. So I need to move this via so that it can make contact with the 3.3 volt copper zone. This can be fixed simply by dragging this via and I'll place it here. Just fix this line and also this area here, because it's a 90-degree turn, which is not a good idea. All right, so that's it. Just going to type the B key to refill the zone, and I've got 100 warnings now. If I run the DRC again, it should be one less. Yeah. Then I've got an issue with the clip of the edge cuts. So U3, which is the ESP32, has got this line which belongs to the Silkscreen that is actually cutting through the edge cuts, and that's a violation. It's not dangerous, of course, and there is no problem with the manufacturing, but again, it's part of the design of the ESP32 footprint. So once again, I am going to select this specific violation to be excluded, and there are two of them, I believe. Three, yeah, so exclude this one as well. There's a few others now. Let's see here. Footprint does not match. Yeah, okay, so this particular footprint for the button does not match the one that is stored in the library. This is not a problem for me because what I'm looking at is correct. So it doesn't really matter to me exactly what the difference is between this version and whichever version is stored in the library. So I'm going to exclude both of these violations. Next up, same issue with ESP32 C3. I'm going to exclude this. I'm going to exclude this as well. Same issue. Now I've got a lot of violations relating to the size of the text. There's really a bunch of them. So what happened here is that I made this text too small. And I can have a look at the capabilities of the manufacturer when it comes to text. All right, so according to this, the minimum line width is 5 mils. It's a minimum. So that's 0.12 millimeters. And the maximum text height is 0.76 millimeters. So if I look at what I've set the constraints to be for the Silkscreen, I've set it for 0.8, the minimum text height, which is correct. And the thickness, set it too small. So this should be 0.12. Having fixed that in my constraints, and now I need to fix all of the text. So I need to fix all the reference text labels. So let's go to edit text and graphics properties. And everything that is on the front Silkscreen, there is a reference designator. I'm going to change the text width to be 0.8, the height to also be 0.8, and the thickness, as small as I can make it within the capabilities, is 0.12. So I'm going to apply this to all of them, and they'll close. So that made all the text bigger, and I'm going to have to make it fit properly, but at least it removes all those violations, and I know that it will be properly printed by the manufacturer. Now I've got a bunch of other things, again, probably because of what I've just done. And you can see here one example, Silkscreen clipped by solder mask. So now I've got Silkscreen on the solder mask and on the pad. So I need to move things around. So I'm going to remove the groups so I can move things around and start moving all the text off the solder mask or the pads. Okay, I think I got them all. Let's repeat the check to see if I missed any. 3 warnings. Oh, I missed one here. Let's move that out here. Actually, move LED there and C3 here. All right, there's a couple of items that requires me to ungroup so that I can grab C1 and I'll place it here. There's one more thing. Okay, this one, Silkscreen clipped by solder mask. So you can see this dot here. This dot actually belongs to the ESP32 footprint. Now to fix it, I'm going to have to actually edit the footprint. Right click on the footprint, click on Open in Footprint Editor. I will need to move this dot somewhere else. Just gonna change the grid and pick that item and move it, say, right there. Save, go back and see if that resolves the issue. Yeah, I think that would do it. So let's do one last check, run DRC. Right, that's fine. As we know, I've just made a change to the ESP32 module, and that is okay to exclude it. Cool. So you can see all the ignored tests in here, so you can add them and then unignore them if you want to. The DRC shows no other issues that I need to deal with, so that means that I can do the last minute improvements, enhancements before going ahead with the design for manufacturing checks. Design for manufacturing checks are all those checks that I will be doing using the next PCB analytics tools that will give me some insights as to whether I've done something that would make manufacturing of the board harder. These are not tests that tell me anything about whether the board itself is functional or not, but whether it actually can be built. So before I do that, there's a few little improvements that I will need to do. Things such as 90-degree angles. This is something that would also be picked by the Design for Manufacturing Analytics tool, but it's so obvious that I'm going to fix it now. And other things such as removing any issues like this one here, like redundant segments of tracks and turns that are not really necessary, and anything else that might pop up actually here. I might even try to reduce the length of some of the longer tracks as I go. So I'm going to start with this. It's quite obvious. So make sure that I can select tracks and vias. Sometimes it's just easier to redraw a track. And I'll draw it with a much thicker track. I'll do the same thing here. Okay. This is redundant, that can go straight in like this. Okay, yeah, I think that is good. I'm going to save. Next up, I'm going to do design for manufacturing checks. These are the checks that help make sure that the board is fit for manufacturing and there's no issues in it that may delay or maybe even make impossible manufacturing. PCB design itself is fine as far as the electrical design rules checks are concerned. However, that doesn't mean that it can be manufactured. That's where the DFM check comes in. For the DFM check, I'm going to use a free tool that is available from Next PCB that you can use it both online or as a Windows application. Next PCB has a version of the DFM checker as a plugin that I've installed, and you can see it right here. But the problem is that this plugin doesn't seem to be working properly with the release candidate 2 version of KiCad 9. It doesn't actually work, so I'm not going to bother with it at all. I'm just going to do all of the DFM checks using the Windows application. The thing to remember is that the Windows application is more capable compared to the KiCad plugin. But the nice thing about the KiCad plugin, once it's back online for KiCad 9, once KiCad 9 is actually released and the plugin works, is that it's embedded in the KiCad environment and you'll be able to do any required changes on the fly without having to go back and forth between the Windows DFM tool and KiCad. Before I get started, just also wanted to show you that you can download your copy of the HQ DFM tool from this page here on the Next PCB website. To make this work, before I go to my Windows virtual machine where I have installed the analysis tool, you need to export the Gerber files from KiCad. There's the plotter button that allows you to export Gerber files, or you can do this via File, Fabrication Outputs, and Gerber files. So I'm going to create our output directory. I'm just going to call it ESP32 Project Gerbers. The layers included are fine as they are here. I'm only going to set proto file name extensions and click on the blue plot file and refill here. The other thing is to generate the drill files for any holes or vias. Click generate again and close. And here is the project directory, and you can see my Gerber files right here. So next up, let's go to Windows. I am going to copy the directory across so that I can import it into the analysis tool. Here it is. And there's the Gerber files. So I'll start the analysis tool, and I'm going to drop all of these files in the Layers tab. And that does the analysis very quickly, all done. It's quite an interesting piece of software, actually, if you want to spend a bit of time exploring it. I do have a blog on the Tech Expressions website that talks about this in a little bit more detail. That includes a video. Shows you things about the reports that can come out of this. But let's go straight in it to see what it does. There's a 3D view as well, which actually is quite nice. Nice work. All right. So here you can see the results. Anything that's green, obviously, nothing to worry about. Anything that is orange, maybe have a closer look at it, but definitely things that are red, you need to check. For example, let's go for the annular ring size. Click on the red button to check it, and the tool will pan exactly where the problem is. Now, this is focusing on the ESP32 ground pads and pins, and there's nothing that we can do about this because this is just what the ESP32 ground pins are like. So there's nothing I can fix here. So what the tool is saying here is that in this particular instance, there is a via with an annular ring that is 1.95 mils in size, and it's telling me that it should be over 5 mils. If I look at the actual one, which is this one right here, clicking on it takes me to these properties, and the diameter is 0.5 mils, the hole is 0.3 millimeters, the difference is 0.2. So 0.2 is actually sufficient because the 5 mils, which is 1,000th of an inch, is equal to 0.127 millimeters, which means that this annular ring is actually bigger than the minimum. Based on that, I'm not going to do anything about this. I'm just going to leave it as it is. Moving on to the PTH annular rings. Again, here there's one that is belonging to the USB port. It's this one here. And again, this is design geometry of the USB port, and I'm not going to do anything about it. Next is the drill to copper. These are actually all things that I can fix quite easily. So there's these, and there's that. So via to trace and PTH. So let's do these first. So I've got via to trace outer. You can see this right here. This via is too close to this track here. So I'm just going to move it down a bit. Just like that. And that will take care of that issue. Next one is this one here with this via right there. So I'm simply going to move it a little bit to the left. And that will sort it out. Okay, next one. This one is this. So this is easy to fix again. Just add a bit of space. Like this, away from the via. That's done. And one more, I think. Yeah, this one here, right here. So move that out a bit towards the left. And that will sort it. Done. Moving on, NPTH. I think this is fine, so I'm going to leave this alone. Drill to copper, done. Moving on, copper to board edge. So this is the edge is a bit too close to the board. So the copper fills are apparently too close to the edge in the inner copper layers. So this I may be able to fix quite quickly by looking at the zones. Select all of those and change the clearance according to the tool. The clearance common is 0.2 millimeter. So let's put a 0.2 millimeter here. Okay, 0.2 millimeters and refill everything. Okay, now that gap is bigger. Okay, let's continue. Next one up is the drill spacing. And okay, these are again issues that have to do with the geometry of the USB connector. There's nothing really that I can do about, but I've checked with Next PCB and this is not a problem for them to manufacture. This is it with the DFM check. Next up in my to-do list is to continue working on the Silkscreen. So the Silkscreen will contain text and some graphics to improve the usability of the board by providing information to the user for things such as what each one of those pins are, or what kind of component is this to help with assembly, information about the version of the board, perhaps a website URL for information on software and example applications and so on. So anything that is useful can go on the Silkscreen. I'm going to be working predominantly on the top Silkscreen, but remember that there's a lot of space on the bottom side of the Silkscreen that you can put more text or graphics. By the end of this process, I'm going to have something like this, an example of what the end result of my Silkscreen work will look like. You can see in this case, I actually removed a couple of mounting holes to make space for the text and for the graphics. In essence, what I did was to add explanatory text, like up here for the role of each of the pins. I used lines to create borders around components that belong together. So for example, all of those components belong to the sound sensor. I've got some information about the role of the LEDs here, what each one of those LEDs does, so that you know what it is when you look at it. And that's pretty much it. There's a couple of logos here as well. I'm going to go ahead and do that work now. I've decided to remove those mounting points because I think that the Silkscreen is more important than those mounting points. So let's go to the front Silkscreen. I'm going to remove this and this mounting holes because I need this space to provide some information about the LEDs. Another thing that I'm going to do before I fast forward this part of the video is that I'm going to select these text items and hide them because I'm going to replace them with new text items that describe the use of the LEDs. So these I'm going to make them disappear. So these are not visible anymore. I'm going to do the same thing with, there's two more LEDs. So there's also this and this LED text items to make invisible. I'm also going to remove that ref. That's not going to be visible either. No need for that to be visible. And that's pretty much it. So the first thing is I'm going to start with the borders. I like, especially because this is a practice board, like an educational board. I like the idea of creating borders around the functional components that belong together and implement a particular function on the board. So anyone who is learning about PCB design and using this board as an example will be able to look at it and know immediately what the various sub-circuits on this board do. I will pick the line tool and create a border around the components that belong together. I'm going to go for 0.1 millimeter just to make it easier to draw. Okay, start here. Up to here, and up, and close that box. Take text box and put that and name this box charger. I'll place it in here. I can actually give it a 45-degree angle. Actually, it should be minus 45 degrees. You can play around with the angle to make it fit nicely with the line. Next, I'll create labels for those LEDs here. So the first one is for charging power to indicate that charging power is okay. The other one here is that the battery is charged, and the third one is that the battery is charging. That's why I made some room up here by removing the mounting hole. So again, pick up the text tool, and the first one is going to be charging power. Okay, and it's always a challenge to make this fit. So let's make this 90 degrees so that I can mount it in like this. And that's done. And I'll continue with the rest. For example, I'm going to go up here and add some text for the role of these pins. I use the same geometry for the text. So this first one is going to be GND. I'm going to continue along the same way, but to save us all a bit of time, and especially you, I'm not going to record this whole process, and I'm going to come back in your time in just a few seconds. In my time, it's going to be probably around 30 to 40 minutes when I would have completed the Silkscreen. And that's it with the Silkscreen. Let's have a look. I'm going to disable some of these layers, take a better look at the Silkscreen layer. So I've got all the borders between the different sub-circuits, got a couple of logos as well. There's always room for the Tech Explorations logo and the KiCad in the back Silkscreen layer. You can also have a look at the 3D view, and there's our board. Actually looks quite nice like this. Which brings me to the next item in my list of items to do, and that is to populate the missing components here for a full 3D render of this board. So let's get into it now. In the current 3D model, you can see that there's a few components that are missing. The most important ones actually, ESP32 is missing, the SD card reader, the USB module, all these things are missing. It's not going to take long to add them. Remember that when I set up this project, I already collected the 3D models for these important components, and for other components such as the polyfuse here, the LEDs, some of the capacitors as well, and even the microphone, I'll be using components that come with KiCad. So I'll be looking at KiCad's own 3D model libraries. Let's start with doing this work. The first thing to do is to set up all the components that don't have a 3D model, whose model is in KiCad's own libraries. That will save me the trouble of having to go to two different places back and forth. And I'm going to leave the 3D viewer open so that it gets updated as I configure each of the components with its 3D model. Let's begin with the microphone. So double click on the microphone, bring up its 3D model. So for the 3D model of the microphone, I'm going to go to KiCad's own libraries. You can see I'm working in KiCad 9 RC. And in here, there's 3D models. And look for sensor. Of course, when you do this for the first time, you need to spend a bit of time to explore. It's unlikely that you'll be able to find what you're looking for immediately. There's no search function, so you really have to browse to find what you need. So I've already done that, of course, so I know where to go. Sensor, audio, and I'm looking for POM. There's two versions of the same model. One is step, the other one is WRL. I just go with step. There's that. And then I need to rotate it a little. So I'm just going to lift it off first. I'm going to add to the offset. I'm going to put it up for the time being and then do a rotate because I want to be able to see its pins as I'm rotating. Like that, actually on the side. Yeah, I need to go like this. All right, and then let's fix its pins. Okay, let's go to the offset now and go down and then a little bit this way. And that's it. And finish up with a Z offset. Done. And there's the microphone. Cool. Let's continue. I'll do the LEDs next because there's a few of them. The first one is power For the power LED, and for all of the LEDs actually, I'm going to use the same model for simplicity. There's no need to change here. So here in this list, there will be an LED SMD, this one here. And there's a few options. You can see what they look like. You can have a look at them and play around. I'm going to be pretty brief with this exploration and just go for the 1206. That seems to be the right size. 1206 here. There's the castellated version. But I'm just going to go with the simple one. This one here looks good. So, okay. That looks nice. And for the others, instead of having to browse, I'm just going to copy the path to the step file. So just click and copy and go to the other LEDs. You can search for LED in the footprints here. So one by one, add those LEDs in here, remove whatever may be in the 3D models list, and then just click on the plus button to bring up the field, and then copy, paste, and hit OK. Continue with the next one. Double click and repeat the same process. And there's our LEDs. I'll do the polyfuse next. It's a large component. Right here. Remove whatever might be there, and let's go through the list here. So we're looking for the fuse 3225. Yep, that's the one. It fits nicely. Hit OK. Another thing you can do if you want to know what's remaining to be fixed is click on this button here, missing 3D models, and that will have a look to see what models are missing. And you can see it picked up 61 missing models, and it created a file, so you can use that file to quickly, in here you see missing 3D models. I'm going to open it up with the text editor, and there's the models that are missing. So there's quite a lot of models missing, but again, don't let that scare you. In this particular case, what's happened is because I'm working with KiCad 9 and KiCad 8 at the same time, I've got this path that doesn't exist in KiCad 9 release candidate, but somehow it found its way in this file. So I'm going to show you a way to fix this problem really quickly and easily, because the thing is that once I fix this variable, then the path is correct and KiCad will be able to grab the missing 3D models. All right, so to fix that, go back to the main KiCad window and under Preferences, go to Configure Paths. In here, you'll see that I've got a few environmental variables, but one that is not in here is the one that I actually need for this particular case. Now, if you're working in KiCad 9, the final version, and you're not mixing KiCad 8 and KiCad 9 like I am, you're not going to have to worry about this. But I'm showing you this because it's an opportunity to show you what you can do with the paths configuration window here to fix this very specific problem. So here, I'm going to add a new row, add the variable that I want to add, and I am going to click on this path, copy it, and paste it, because I know that this actually exists. This is what I'm picking up, all of the components and the 3D models that I showed you so far. So essentially, I'm going to have these two variables that are pointing to the same place, and that is going to fix the issue with these missing 3D models. All right, so now let's do the check again. Only 6 missing. Perfect. So we fixed most of them. And the ones that I need to fix, I'm just going to reopen this file, have to do with legitimately missing 3D models. Not sure why the format didn't work out this time around, but let me just do this one more time. Just going to delete it. Going to delete this too and do the check again. Okay, 6. Never mind. It's fine. So what's missing is C4, C3, C9, there's U4 there, C7, C12. So these are the tantalum capacitors. First is C4. I'm just going to search for that. So C4, double click on it. And this capacitor is in the built-in 3D models. We go for capacitor SMD, capacitor tantalum. Actually, that's what I need. Go in here, look for CPEIA, The size is 3216, 18 Kemet. This one right here, I'll go for this step. Model, done. And you can remove the other one there. So now I'm going to copy this, hit OK, and let's look for the others. So the next one is C3. Just like what I did with the LEDs, I'm going to repeat the process here. There you go. Should probably put a slightly larger capacitor there for the tantalum, but it's okay. Then it's C9. Then it's C7. And that's it with the capacitors. All right, so all the capacitors are there. C4, C7, and so on. It's not that these are missing, it's that they're not configured correctly. That's why they're coming up. There's other components that do have missing 3D models, but they're not listed in this list because they just haven't been configured. And the next one is U4 that is also misconfigured. So let's look for that. U4, this one here. And for this, I'm going to look in the built-in libraries. I'm going for the package DFN. And then in here, I'm looking for QFN16. It's one of those over here. 1EP, 3x3, 0.5 millimeters, 1.8 by 1.8. This one right here. Step. Yep. Okay. Done. And it's properly aligned as well. If I do another check, you'll see that there's one missing. U4. I thought I just added that, didn't I? Oh yeah, it's because I didn't delete the original. So let's delete that, hit OK, save, and let's check again. Models missing, 0. However, if we have a look at the 3D viewer, you'll see there's actually some models that don't have configuration. So let's add them. So these are all the models that I have collected at the beginning of the project, and now I'm going to actually assign them to the footprints. Let's start with the connector down here. This one, the model is in the project directory. So let's navigate to the working project directory, and in here is the libraries, the 3D models, and then what I'm looking for is the B2 PH SM4. Let's orient it, so rotate back and forth. There's a bit of playing around with this until I get the right one. That's the one. Next, I'll do the USB port. So this one is the SS5240. Okay, perfect. Let's take a look at what the port looks like now. All right, yeah, making progress. Let's continue with the 2 buttons. The model is USLPT. This one right here. That's the models. It won't fit exactly though, so I'm going to need to fine tune it. And I'm going to copy this because I've got another button. So I'm just going to copy that and assign it to the other button and set the same transformations. Okay. Next up is the SD card. So the model for that is the GSD0 model in this directory. GSD0, yeah, that's it. And that happens to fit perfectly. And I'm going to go up and sort out the model for the ESP32. And the model for this is this one. Done. Let's take a pause and have a look. Yeah. This is looking really nice. Not much more to go. So there's U6, Q1, and VR1 left to do. And the BME 280 up here, U2. So the light sensor, that is the TEM T6000. You can see the pad configuration in the bottom. Now you just need to make sure that these pads are correctly aligned. This orientation is good. So I just need to flip it on the X-axis by 90 degrees. And that's it. Yeah, it's okay. Next, I've got the regulator, LM1117 3.3. So 90 degree flip, done. And I think it was U2 as well. So this is BME280 step. We need to be a bit mindful of pin 1 marked with this dot there against this dot. So you can see where the dot is. So I really need to flip it, I think on the x-axis, actually before the x-axis. Let's go back to where it was because I want to be able to see that dot. Let's go z-axis, 90 degrees. Yep, so that's aligned there. So then x to make it close. That's it. And you can see that dot against that dot there. Let's have a look at what the model looks like now. Have I missed anything? Oh, yep, I've missed U6, but I think everything else is now correct. So let's finish with the flash memory. The flash memory is model IDW25Q32. Okay, and simply a 90 degree on the x-axis would do. All right, so let's have a look at the final result of all this work. There's the board. It looks amazing, in my opinion. This gives you a really good idea of where things are, what the final result is going to look like. If the user interface is reasonable and workable, even if the test points are where they should be, there is room to make changes here. And even at this point, those changes are not necessarily painful. You will be able to make, oh, you just noticed one more, the amplifier here, one more component is missing. So let's do that. The amplifier from memory, let's see. So the amplifier is the MAX4466EXK. Flip that on the x-axis. Yep, and that's it. Have a look one last time, and there's the amplifier. And I think, yeah, now everything is where it's supposed to be. The PCB is now ready to export from KiCad and import into your manufacturer of choice. In my case, I'm going to go ahead with the order and the assembly through Next PCB. Let's have a look at what that looks like. On the Next PCB website, let's go back to the home page just to make this easy to follow as possible. When you go to the Next PCB website, you've got a couple of options you see under PCB service. The first one is to get a quote for a PCB only without any components assembled on it. And the other one is to go for the full assembly. If you go for the quote, all you've got to do is to upload the Gerber files. If you go for a assembly though, things are a little bit more involved because you've got to upload the Gerber files, plus there's a bunch of files for the assembly part of it. I'm going to go through the PCB assembly quote process very quickly with you now. First thing to do, of course, is to start with the Gerber files. And since I've made a few changes to the PCB since last time I exported my Gerbers, I'm going to go and do that again. So click on the plot file. Everything is already selected. Just going to use the same output folder, and the new files here that I'm about to generate will overwrite the old files, and that's okay. So click on plot. So yep, refill the zones. That's done with the layers, and then the drill files, same thing, generate, and that's done. Then let's go to the project directory, and here is the Gerber files. And I'm going to create a zip file from the Gerbers because that's how Next PCB, and actually in this case most manufacturers, want the Gerber files to be bundled inside a zip file. Now let's head over to the website. So here I just need to drop the Gerber files. If I can do a drag and drop, that should work. Yes, it did. I'm using Safari here, and I've also done this with Firefox and Chrome. It all works. The backend Next PCB, the website, will analyze the files and gives me a view. I can have a look at the view, or I can also go to the Gerber viewer, the online tool that they have here, analyzing the files. I didn't have to re-upload them. It's very convenient. And then it gives you one more chance to have a look around and make sure that nothing has been missed. Have a look at the layers. This is what Next PCB is going to work on. Remember, they don't have access to KiCad. They only have access to the Gerber files that you just sent them. I've already done a lot of checking, so I'm not going to do any more. I'm going to go back to the first step of the process. Here, select the various parameters. Next PCB already detected that I've got 4 layers, which is correct. It's detected the dimensions. I can choose here how many copies of the PCB I'd like to have. Any other parameters, color, PCB thickness, I just go with the standard, whatever is standard here, I'll go with that. Anything else you check here will have an increase in price. And let's say that you're happy with this. Next step is step 2, which is the assembly. So now 2 additional files are needed. The first one is the Centroid file. The Centroid file is a data file used in electronics manufacturing to provide precise information about the placement of components on our PCB. It's also known as a pick and place file or XY data file. You need to first export it from KiCad before you can upload it to next PCB. So let me show you how to do that. You go to File in the PCB editor, then Fabrication Outputs. Look for component placement, POS or GBR file. Click on that. I'm just going to leave the output directory as this. This is the home of the project directory and nothing else is needed. Just generate the position file. That's it. 81 components, information. So I can close this and then have a look at the new file that was just generated. Let's see, it's this one right here. One for the bottom and one for the top. The one for the bottom doesn't have any information in it because there's no components on the bottom side. But the top side has components, so there's data in here. It looks like this. So the components, its reference, its value, the package, and the exact position, whether it's rotated or not. You can see it's all top side. So I'm going to take this file and upload it to next PCB. It says that I need to zip this file up, even though it's a single file. I'm going to do so, just compressing it into zip and upload it. It's done. So how many copies would I like? Let's say 5. Then they need the BOM file, the bill of materials file. Here is my bill of materials. There's a lot of information in here, but it's actually not that difficult and time consuming to put this file together. You can get all the information that you need from EE Schema. So in EE Schema, click on this button here to bring up the symbol fields table. And from here, you can select all the columns that you want to export in the BOM. If you look at the next PCB instructions, they need a number for the row, a designator, quantity, manufacturer, part number, procurement type, and customer node. And you can download a template as well. So you make sure that all of these columns exist in your table, and you can enable or disable these columns by clicking on these boxes. And then go to the Export tab and you can export it from here. So I've already done this, and this is the BOM file that I've already actually sent them. It's got the information that they need plus more information, especially the description is very important because I can include things such as the source of a particular part. You can see here I've got Snapita where I sourced and verified that this particular component is in stock, and I've done this with other components as well. Let's go back to the website and upload the file here. And the thing to remember as well, I know there's a lot of things to remember, but one more thing to remember, it's okay, I can just continue with whatever I have uploaded, is that there are people on the back end that are going to look at these files and provide you with feedback and then, of course, ask questions. My order is ready to go. It doesn't mean that this order is actually going to go through. The production engineers will be looking at the Gebe files, the Centroid file, and the BOM to make sure that they can actually produce this PCB. For example, with the BOM file, they will ensure that all of the components needed to go on the board for the assembly are on hand. And if they're not on hand in the warehouse, they'll have to order them. And if they're having trouble sourcing any of those components, they'll get back to you to let you know so you can decide of whether you can source those components yourself or maybe you need to find alternatives. But there's a lot of back and forth communication between you and the production engineers throughout the process. That may take 1 or 2 weeks for the production to actually get started. My production status is now complete and the assembled boards have been sent, but you can see here there is a dashboard that shows where in the process your PCB is. If there's any questions from the engineering team, you'll receive an email with the questions. There are going to be photographs as well. If there's a problem with a particular component, maybe the fit is not appropriate, you'll get a photograph to indicate the problem and to find ways to fix it. And you can see here some of the communications and status changes over the last couple of weeks as this PCB was being manufactured. I also want to show you here the engineering questions page on my Next PCB account, just for you to have a better understanding of what happens once you submit your assembly job. Once the engineers on the Next PCB production floor get a hold of your project files and they evaluate them, the most likely they will have questions. So they will use this page here to communicate with you, and you get email notifications as well to which you can reply, or you can just go in here in this page, have a look at each one of the messages, and then use the forms provided to respond. So of course my project is complete, so you can see all of the messages that appear in this list. So you can see how long the process took, about 10 days from when the first message came to when it was completed. And you can see the first message looks like this. Start down the bottom. This is the whole history here, but you can see the first one was just to show that, they've done a bit of work and they found something that needs to be fixed. In this case here, they attached an Excel sheet. They identified 3 issues that needed my attention. So the first one had to do with 2 resistors and the connector, and it says can't be soldered. Sometimes you just need to read in between the lines here. So they have identified the components in the BOM that I provided. There's a screenshot here, and I like how they use screenshots to just pinpoint where the issue is, so you don't have to wander. And there's a suggestion that's very helpful, added to the pick and place file. After looking at this, I realized that there's actually no J5 component. So what happened here was that there used to be a J5 component, which I then deleted. So there's no J5. That caused the confusion. I just mentioned a bit of history here that J5 was removed after the BOM was submitted. My mistake here that they picked up. And the same thing applies for R17 and R21. So things like that happen. Here's another example that they picked up. J1, switch 1 and switch 2. The issue here is that they don't have a specific part number. They couldn't find the appropriate part number from their BOM that I've sent them. So I was a little confused about this, to be totally frank. So I asked a follow-up question. I understood that they needed me to provide a part number, but I also wanted to double check if there was something in the footprint that I provided that would cause them difficulties with soldering. The response that I got from this was that no, the footprints and the geometry of the pads here was not a problem. They just didn't have the part number. So I provided a new BOM with the part numbers for those 2 components. So the other thing was a bit of confusion as to the cathodes and the anodes of the capacitors and the diodes because of the symbols used to denote cathodes. So in this case, I simply confirmed that where you see a dot in a capacitor footprint or this bracket, Silkscreen drawing, that indicates the anode for the capacitors. So dot is the anode, not the cathode. So there was a problem caught early because they asked the right question. And then for the diodes, this symbol here, the blue bracket graphic, indicates the cathode. So that was sorted out, and it was fairly smooth sailing from then onwards. Here's the next one, asking me for confirmation that the assembled PCB as I see it in these images is correct. And then I had a very close look, took my time to have a look around here. So that was all pretty good. The only thing that I did here was to ask for this particular header to be replaced, just to put in something smaller like the one in J6 instead of this much larger one, because this would make it harder for me to try out different devices on this I2C header because I don't have a plug like this. They were happy to make the switch of this specific header, and then they came back to me just a little while later, a couple of days later, to let me know that's not completed, and just to confirm that there's no other changes I'd like to the board. I didn't have any additional requests, so that was the end of this process. After that, at the beginning of the video, I said I was planning to show you the final manufactured PCB after receiving it from the manufacturer, Next PCB. However, due to shipping delays, and just note that it's Chinese New Year at the moment, plus we had a public holiday in Australia, so all that caused a delay with the delivery, so I haven't received the board yet. But I am on a hectic schedule. I just want to complete this video and not wait for the actual PCB. So there's that. But once I do receive it, I record a follow-up video where I'll unpack and show you what the real board looks like. And I'm also going to be doing a bit of testing. I'll share my impressions of the final product, walk you through the testing process. I've had no idea if it will actually work. I hope it will. I've spent a lot of time testing, cross-checking, and verifying the design just to make sure that I haven't missed anything big. So I'm pretty confident that it will work. But of course, testing is required. I do have high confidence that it will work, but that remains to be seen. To make sure you don't miss that upcoming video, please do subscribe to the Tech Exploration channel right now if you haven't done so already. To quickly recap this very long video, we covered everything here from creating the schematic to managing libraries to designing the PCB layout, routing, performing the various design checks. Along the way, I shared my experiences with KiCad 9 I've been using for this video. KiCad 9 release candidate 1 the beginning, and a little bit later RC2 when it came out, and I was able to take advantage of the numerous improvements in KiCad 9. Along the way, you saw firsthand what it is like to use KiCad 9 to build a PCB like this one, a 4-layer realistic IoT PCB. By the time that you watch this, KiCad 9.0 will be out, and as a community, I believe that we'll have gained an even better open source PCB design tool. So thank you for watching this unusually long video. I truly appreciate your time and interest in this project, and I hope that this video has been helpful in demonstrating the process from setting up the schematic and selecting components to laying out the PCB and preparing it for manufacturing. If you found this content valuable, please consider subscribing to the channel to stay updated on future videos, including, as I said, the follow-up with the manufactured board. And don't forget to like this video and share it with others who might find it useful. Your support and feedback do mean a lot to me, so feel free to leave a comment below with your thoughts, questions, or suggestions. And I look forward to hearing from you.